Voyager 2 is dying, not all at once, not in a violent explosion or a catastrophic crash into some distant moon. It is dying the way a heart gives out after too many years, slowly, quietly, 1 watt at a time. Right now, 15 billion miles from the chair you are sitting in, a machine the size of a small car is losing its ability to speak. Its plutonium heart, the 3 glowing cores that have kept it alive for 47 years, are fading. The decay is patient, predictable, irreversible. And NASA knows exactly when the lights will go out. Sometime in the early 2030s, Voyager 2 will transmit its final signal, a faint whisper across the void, barely strong enough to reach Earth's most powerful antennas. And then silence. Not because it stopped moving. It will still be out there, coasting through the dark at nearly 10 miles per second, carrying humanity's message on a golden record that no one will ever play. But it will be alone in a way nothing human has ever been alone before. No data, no signal, no proof it still exists. This is not a story about how far Voyager 2 traveled. It is a story about what happens when the farthest thing we have ever built takes its final breath. About the instruments NASA is shutting down right now, one by one, to buy a few more months of life. About the interstellar threshold it crossed in 2018, and the discoveries it made that rewrote what we thought we knew about the edge of our solar system, and about the journey it will never complete. The 300,000-year drift through the Oort Cloud, silent and untethered, long after every human who built it has turned to dust. Some missions end with glory. Voyager 2 will simply go quiet. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a machine 15 billion miles from the chair you are sitting in, moving through a darkness so complete that calling it empty would be generous. It has been traveling for almost 5 decades. It has no crew. It has no lights. It carries no fuel that will ever bring it home. And sometime in the next few years, possibly the next few months, it will go silent forever. Not because it crashed, not because something went wrong, but because the universe is large and power is finite, and every machine, no matter how well built, eventually runs out of time. Its name is Voyager 2, and it is dying the way only a spacecraft can die, slowly, quietly, 1 instrument at a time, while still moving forward at 35,000 miles per hour with no way to stop and nowhere to go. When people talk about the death of a spacecraft, they usually mean something sudden, a fireball over the Pacific as a satellite re-enters the atmosphere and burns up in seconds, a crater on Mars where a lander hit the surface too fast and shattered into scrap metal, the twisted wreckage of the Challenger scattered across the Atlantic. Those deaths are visible. They have a moment, a before and an after. You can point to the exact second the machine stopped being a machine and became debris. Voyager 2 will not give us that. There will be no explosion, no impact, no dramatic final transmission with a countdown clock and engineers holding their breath in a control room. One day, the signal will simply stop arriving. The massive radio dishes of NASA's Deep Space Network will point at the coordinates where Voyager 2 is supposed to be, and they will hear nothing. Static, the hiss of the universe itself. And somewhere out there in the black, the spacecraft will still be flying, still intact, still obeying the laws of motion exactly as it has for 50 years. It just won't be talking anymore. That is the loneliest kind of death imaginable. To still exist, to still function in some technical sense, but to have lost the ability to tell anyone you are there. Voyager 2 launched on August 20, 1977 from Cape Canaveral, Florida. It rode a Titan Center rocket into the sky on a trajectory calculated with slide rules and early computers, aimed at a window in space that would only stay open for a few weeks. The mission planners were chasing an alignment of the outer planets that happens once every 175 years. Jupiter, Saturn, Uranus, Neptune, all of them would line up in a grand arc across the solar system, and if you launched at exactly the right moment with exactly the right speed, you could visit all four using gravity assists. Each planet would fling the spacecraft forward like a slingshot, gaining speed without burning fuel, threading from one world to the next in a cosmic game of billiards. The alignment would not come around again until the year 2152. If humanity wanted to visit the outer solar system in a single mission, it had to happen then. It had to happen with the technology available in 1977, and it had to work on the first try. It worked. Voyager 2 reached Jupiter in 1979 and sent back images of swirling storms larger than Earth. It flew past Saturn in 1981, threading between the rings at a distance so close that mission control could see individual ringlets separating like grooves on a record. Then it did something no spacecraft had ever done before. It kept going, past the orbits of the gas giants, out toward Uranus, which it reached in 1986, and Neptune, which it flew past in 1989. By the time Voyager 2 finished its tour of the outer planets, it had sent back more than 5 trillion bits of data, thousands of images, temperature readings, magnetic field measurements, the first close-up pictures of moons that had only ever been blurry dots in telescopes. It discovered new rings around Jupiter and Uranus. It found volcanoes on Io spewing sulfur into space. It mapped the winds of Neptune, which blow faster than the speed of sound on Earth. And then it left. Not because the mission was over, but because there was nowhere left to turn. The trajectory that had carried it past 4 planets was now carrying it out of the solar system entirely. Voyager 2 crossed the heliopause in November 2018, the invisible boundary where the solar wind from our sun finally loses its push and the true interstellar medium begins. It became only the second human-made object to enter interstellar space. Voyager 1 had crossed a few years earlier, and the 2 spacecraft are now the most distant artifacts humanity has ever created. Voyager 1 is about 15 billion miles away. Voyager 2 is about 12.5 billion miles out, still moving, still transmitting, still doing exactly what it was designed to do, until it stops. Here is what makes Voyager 2 different from almost every other mission that has ever ended. Most spacecraft die because they were supposed to. They run out of fuel and crash into the planet they were orbiting. They complete their mission and get shut down deliberately to make room in the budget for the next thing. They get old and their electronics fail, and mission control makes the decision to stop listening. The death is planned. It is scheduled. Someone signs a document that says this is the end. Voyager 2 is not ending because NASA decided to end it. It is ending because physics is patient and entropy always wins. The spacecraft is powered by 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. When Voyager 2 launched, those generators produced about 470 watts of power, enough to run the spacecraft's systems, its instruments, its transmitter, and its heaters, which keep the electronics from freezing in the -200-degree cold of deep space. But plutonium decays, slowly, predictably, unstoppably. Every year the generators produce a little less power. Every year the spacecraft has a little less energy to work with. NASA has been rationing that power for decades. In 2019, they shut down one of Voyager 2's heaters to keep the science instruments running. In recent years, they have turned off other non-essential systems one by one, deciding which parts of the spacecraft can be sacrificed to keep the most important systems alive a little longer. The engineers are playing a game they cannot win. They are trying to delay the inevitable by making cuts, and every cut brings them closer to the moment when there is nothing left to cut. The math is straightforward. At the current rate of decay, Voyager 2 will not have enough power to run even a single science instrument by sometime in the early 2030s, maybe 2032, maybe 2035. The exact year depends on how efficiently the remaining systems can be managed and whether any unexpected failures force an early shutdown. But the window is closing. Within the next decade, Voyager 2 will go silent not because it wants to, but because it will have run out of the electricity needed to send a signal across 15 billion miles of empty space. When that happens, the spacecraft will still be there. The structure will still be intact. The golden record bolted to its side, a message from Earth containing sounds and images and greetings in dozens of languages, will still be there. The cameras, the magnetometers, the plasma detectors, all of it will still be physically present. But without power, none of it will function. Voyager 2 will become a tomb, a perfectly preserved artifact, drifting through interstellar space, carrying the last intentional message humanity ever sent beyond the solar system, with no way to tell anyone it still exists. That is the death we are watching unfold in slow motion. Not a crash, not a failure, just a slow fade into silence. The fact that we can hear Voyager 2 at all from that distance is borderline miraculous. The spacecraft transmits at 23 watts. That is less power than a refrigerator light bulb. By the time that signal crosses 12.5 billion miles, it has spread out so thin that when it finally reaches Earth, the total energy arriving is measured in billionths of a watt. If you collected every photon of radio energy that Voyager 2 has ever sent back to Earth and converted it into heat, it would not be enough to warm a cup of coffee. NASA listens for that whisper using the Deep Space Network, a collection of massive radio antennas scattered across 3 continents. These dishes are among the most sensitive listening devices ever built, capable of detecting signals so faint that they are drowned out by the thermal noise of the universe itself. And even with that level of precision, Voyager 2's transmissions are right at the edge of what can be detected. A few more years of power loss, a slight drift in the spacecraft's antenna alignment, and the signal will drop below the threshold where it can be distinguished from background noise. At that point, Voyager 2 might still be transmitting, but Earth will no longer be able to hear it. That almost happened in 2023. In late July of that year, NASA sent a routine command to Voyager 2 as part of a planned series of operations. Someone made a small mistake. The command sequence accidentally included an instruction that tilted the spacecraft's antenna 2 degrees away from Earth. 2 degrees. That is roughly the width of your thumb held at arm's length. It does not sound like much. In the context of interstellar space, it is catastrophic. Voyager 2 went silent. For 2 weeks, NASA heard nothing. The spacecraft was still there. It was still flying. It was still transmitting, but the signal was no longer aimed at Earth. It was spraying out into empty space in a direction where no one was listening. Engineers at the Jet Propulsion Laboratory scrambled. They recalculated the spacecraft's position. They adjusted the pointing of the Deep Space Network antennas, trying to pick up any stray signal that might have scattered in Earth's direction. And on August 1, they found something. A faint carrier signal too weak to contain any real data, but strong enough to confirm that Voyager 2 was still alive and still operating. That detection buoyed spirits, as NASA's project manager later put it, because it meant the spacecraft had not failed. It had not been hit by a micrometeorite. It had not tumbled out of control. It was simply pointing the wrong way, and if it was still functioning, there was a chance NASA could fix it. The problem was distance. Voyager 2 was so far away that any command sent from Earth took 18.5 hours to reach the spacecraft. The response, if it worked, would take another 18.5 hours to travel back. 37 hours round trip. If the engineers sent the wrong command, they would not know for more than a day and a half, and by then it might be too late to correct. They had one shot. On August 4, NASA sent the command. It was a simple instruction: reorient your antenna, point it back at Earth. The command traveled outward at the speed of light, crossing the orbits of the planets, crossing the heliopause, crossing 12.5 billion miles of interstellar space. 18.5 hours later, it arrived. Voyager 2 received the instruction. Its thrusters fired. The spacecraft rotated by 2 degrees, and 18.5 hours after that, the signal came back. Full contact restored. The spacecraft was talking again, but the scare was real, because that 2-week silence was a preview of what is coming. Someday soon, Voyager 2 will stop transmitting, not because of a mistake, but because it has run out of power. And when that happens, there will be no command that can bring it back. The silence will be permanent. There is something deeply strange about mourning a machine. We do not usually grieve for objects. When a car stops working, you replace it. When a phone breaks, you buy a new one. We do not hold funerals for toasters, but Voyager 2 is different. Maybe it is because of how far it has traveled. Maybe it is because of how long it has survived. Maybe it is because somewhere along the way we stopped thinking of it as a machine and started thinking of it as an ambassador, a representative of humanity sent out into the dark with a message we knew would probably never be read, but felt compelled to send anyway. The golden record is the most human thing we have ever done. A 12-inch gold-plated copper disc etched with sounds and images from Earth, mounted on the side of Voyager 2 in a protective aluminum case. It contains greetings in 55 languages. Music from Beethoven, Chuck Berry, and traditional folk songs from cultures around the world. Sounds of wind, rain, thunder, whales, a crying baby, a kiss. Diagrams showing where Earth is located relative to nearby pulsars. Instructions on how to play the record, assuming whoever finds it has figured out how to build a turntable from scratch. The whole thing is absurd when you think about it. The odds of Voyager 2 ever being found by an intelligent civilization are so astronomically low that they might as well be zero. Space is unimaginably large. The spacecraft is unimaginably small. It is traveling at 9.6 miles per second relative to the Sun, which sounds fast until you realize that at that speed it would take more than 19,000 years just to cross a single light year. The nearest star system is over 4 light years away. Voyager 2 is not headed toward it. Even if it were, it would take more than 70,000 years to get there. And even if it somehow reached a star with planets, and those planets had life, and that life was intelligent, and that intelligence was curious, the odds that they would notice a tiny metal object drifting past their star system are functionally zero. The golden record was never really meant to be found. It was meant to be sent, because the act of sending it mattered, because we wanted to believe that even if no one ever hears it, the gesture itself means something, that somewhere out there, carried by a machine we built with our own hands, there is proof that we existed, that we made music, that we loved, that we tried, and now that machine is running out of time. Voyager 2 is not just a scientific mission, it is a statement about what it means to be human. about our need to explore, to reach beyond what we can touch, to leave something behind that lasts longer than we do. And the fact that it is dying, slowly, inevitably, unreachably far away, makes the whole thing unbearably sad in a way that has nothing to do with science and everything to do with the fact that we sent a piece of ourselves into the dark and we are about to lose contact with it forever. The spacecraft is still moving. Right now, as you read this, Voyager 2 is traveling farther from Earth. Every second, it covers 9.6 miles. Every hour, it crosses more than 34,000 miles. Every day, it adds another 800,000 miles to the distance between itself and the planet that built it. It will keep moving for millions of years, long after its power runs out, long after its transmitter goes silent, long after every person who worked on the mission has died, long after the civilizations that launched it have changed beyond recognition. Voyager 2 will still be out there, drifting through the galaxy, carrying the golden record, carrying our voices, carrying the memory of a species that once looked up at the stars and decided to reach for them. But we will not be able to hear it, and it will not be able to hear us. And that, more than anything else, is what makes this mission so profoundly lonely. Voyager 2 is not ending because it failed. It is ending because it succeeded so completely that it flew beyond the point where we could follow. The machine that powers all of this, the plutonium heart that has kept Voyager 2 alive for nearly 5 decades, is the only reason any of this is possible. Without it, the spacecraft would have frozen and died within months of launch. But that heart is fading, and when it finally stops beating, the most distant voice humanity has ever sent into the universe will fall silent forever. The machine that has kept Voyager 2 alive for nearly 5 decades is a masterpiece of nuclear engineering built by people who understood a simple, uncomfortable truth. If you want to explore the outer solar system, sunlight will not save you. At Earth's distance from the sun, solar panels work beautifully. They are lightweight, reliable, and they convert light into electricity with enough efficiency to power satellites, space stations, and rovers on Mars. But the further you travel from the sun, the weaker that light becomes. By the time you reach Jupiter, sunlight has dropped to 4% of what it is at Earth. At Saturn, it is 1%. At Neptune, where Voyager 2 flew in 1989, sunlight is less than 0.1% of the intensity we receive on Earth. You would need solar panels the size of a football field just to power a single instrument. And even then, you would be one dust storm, one micrometeorite strike, one minor malfunction away from total mission failure. The engineers designing Voyager in the early 1970s did not have the luxury of hoping for better solar panels. They needed a power source that would work in the dark, in the cold, in the complete absence of anything resembling environmental support. They needed something that would run for decades without maintenance, without sunlight, without fuel deliveries from Earth. They needed a battery that could outlast every moving part on the spacecraft, and they found it in one of the strangest places imaginable: nuclear decay. At the heart of Voyager 2 sit 3 devices called radioisotope thermoelectric generators. The name is a mouthful, but the concept is almost elegant in its simplicity. Take a chunk of plutonium-238. Not the kind used in bombs, that is plutonium-239, but a different isotope that decays through heat rather than fission. Plutonium-238 produces no explosive chain reaction. It just sits there, quietly breaking apart one atom at a time, releasing heat as it does. Wrap that plutonium in thermocouples, devices that convert temperature differences directly into electricity, and you have a power source that asks nothing from the universe except time. Each of Voyager 2's 3 RTGs contains about 7.5 pounds of plutonium-238 pressed into ceramic pellets and sealed inside iridium cladding. Iridium is one of the densest, most corrosion-resistant metals on Earth. It can survive re-entry into the atmosphere without breaking apart. It can withstand impacts that would shatter steel. The cladding is there to make sure that even if something catastrophic happens during launch, a rocket explosion, a crash, a fireball, the plutonium stays contained. No one wanted to scatter radioactive material across the Florida coastline because a Titan rocket had a bad day. When Voyager 2 launched in 1977, those 3 RTGs together produced about 470 watts of electrical power. That is roughly the output of 5 old-fashioned incandescent light bulbs. Not a lot of power by the standards of modern electronics. Your microwave oven uses more than twice that much energy just to reheat leftovers, but in space, where every watt counts, 470 watts was a fortune. It was enough to run the spacecraft's computers, its transmitter, its cameras, its magnetometers, its plasma detectors, its heaters, and still have a little left over for redundancy. The problem, and this was always the problem, is that plutonium-238 decays. That is the entire reason it works as a power source, but it also means the power output drops over time. Plutonium-238 has a half-life of about 87.7 years. That means every 87.7 years, half of the remaining plutonium atoms will have decayed into uranium-234, releasing heat as they go. After 87.7 years, you have half the plutonium you started with. After another 87.7 years, you have half of that. The decay curve is exponential, which means it drops fast at first and then slows down. But here is the thing that makes the math uncomfortable. Voyager 2 does not have 87.7 years to work with. The power loss is not just from radioactive decay, it is also from the gradual degradation of the thermocouples themselves. These are physical devices, tiny junctions of dissimilar metals that generate voltage when one side is hot and the other side is cold. Over time, those junctions degrade. The metals diffuse into each other. The temperature difference becomes less efficient at producing voltage. The system loses power faster than the half-life alone would predict. The commonly cited figure, though NASA does not publish an exact annual number, is that Voyager 2 loses roughly 4 watts of electrical power every year. 4 watts does not sound like much. It is the power draw of a single LED bulb. But compound that loss over nearly 5 decades, and you are looking at a spacecraft that has lost close to 200 watts since launch. Nearly half its original power budget gone. Not because anything broke, not because any system failed, just because time moves forward and entropy does not take days off. Picture it this way. When Voyager 2 flew past Jupiter in 1979, it had enough power to run 11 scientific instruments simultaneously, plus the cameras, plus the transmitter, plus the heaters that kept the electronics from freezing in the 300-degree below zero cold of deep space. By the time it reached Neptune in 1989, the power budget had tightened. Some instruments were being cycled on and off to conserve energy. By the time it crossed into interstellar space in 2018, the spacecraft was running on fumes. And by 2024, NASA had already shut down multiple instruments permanently, not because they stopped working, but because there was no longer enough power to keep them running. That is the slow death we are watching. Not a failure, a managed decline, and the people managing it are doing so with the kind of precision you would expect from engineers who have spent their entire careers keeping a machine alive long past its design life. The decisions are brutal. Every year, as the power drops, NASA's Voyager mission team gathers and reviews the spacecraft's remaining energy budget. They calculate how much power is left. They project how much will be available next year and the year after that. And then they decide what gets sacrificed. In November 1998, more than 20 years after launch, the team shut down the ultraviolet spectrometer and several other instruments permanently. The spacecraft had finished its primary mission. The grand tour of the outer planets was complete. Everything from that point forward was bonus science. But to keep getting that science, they had to start making cuts. The ultraviolet spectrometer was the first to go. It had done its job. It had mapped the atmospheres of the gas giants. There was no ultraviolet light worth measuring in interstellar space, so the instrument was turned off to save power for things that could still produce useful data. In 2024, the plasma science instrument was shut down. This one hurt. The plasma science instrument was specifically designed to measure the charged particles flowing through space, the solar wind inside the heliosphere, and the interstellar plasma outside it. It was one of the key instruments for understanding what interstellar space actually looks like. But it drew power, and there was not enough power left to run everything. So the plasma science instrument was turned off, and the mission kept going. In 2025, the low-energy charged particles instrument was terminated, another loss, another piece of the spacecraft's scientific capability stripped away to buy a little more time for the remaining instruments. And according to the mission timeline, the cosmic ray subsystem is scheduled to be shut down in 2026. These are not easy calls. Each instrument represents decades of work. Engineers and scientists spent years designing them, testing them, calibrating them. Some of these instruments are the only devices of their kind ever sent into interstellar space. Shutting them down means losing data that can never be replaced. But the alternative is to let the entire spacecraft die sooner. So the team makes the cuts. They prioritize, they choose which instruments are most scientifically valuable and keep those running as long as possible. Everything else gets sacrificed. The heaters are the other major power drain. Voyager 2 was not designed to operate in deep space. It was designed to operate near planets. The electronics inside the spacecraft have temperature tolerances. If they get too cold, they stop working. Some of them crack, so the spacecraft carries small electric heaters that keep critical components warm enough to function. Those heaters draw power, a lot of power. And as the RTGs have faded, NASA has been turning off heaters one by one, allowing parts of the spacecraft to drop to temperatures they were never designed to reach, and hoping the electronics keep working anyway. In 2019, the team turned off a heater that was warming one of the spacecraft's subsystems. The electronics kept working. They got lucky. They are still getting lucky, but luck runs out. At some point, a component will get too cold and it will fail. And when that happens, the mission team will have to decide whether to turn the heater back on and lose something else, or let the failure stand and hope the spacecraft can keep operating with one less working part. This is what engineering at the edge looks like. Not building something perfect, not designing for every contingency. Just making the best call you can with the information you have, knowing that every decision is a trade-off and that the clock is running. The RTGs themselves are marvels of Cold War engineering. The United States developed radioisotope power systems in the 1950s, originally for military applications, remote weather stations in the Arctic, navigation beacons in the middle of the ocean, places where you could not run a power line and could not rely on batteries. The early RTGs were crude, inefficient, and sometimes dangerous, but they worked. They sat in the middle of nowhere for years, quietly producing power, asking nothing in return. By the time NASA started planning deep space missions in the 1960s, RTGs had matured into reliable power sources. The first spacecraft to carry one was Transit 4A, a navigational satellite launched in 1961. It worked, the technology proved itself, and from that point forward, every NASA mission venturing beyond the orbit of Mars carried RTGs. Pioneer 10 and 11, which explored Jupiter and Saturn in the 1970s, Voyager 1 and 2, Galileo, which orbited Jupiter for 8 years, Cassini, which spent 13 years at Saturn, New Horizons, which flew past Pluto in 2015 and is still operating in the Kuiper Belt, all of them powered by plutonium. The alternative would have been to develop nuclear reactors for space. The Soviet Union tried that. They launched dozens of radar satellites powered by small fission reactors in the 1970s and 1980s. Some of them worked. Some of them failed catastrophically. In 1978, a Soviet satellite called Cosmos 954 re-entered the atmosphere over northern Canada and scattered radioactive debris across hundreds of miles of tundra. The cleanup cost millions of dollars and created an international incident. The United States looked at that outcome and decided that RTGs, which produce no fission and carry much smaller amounts of radioactive material, were the safer bet. The plutonium itself is the bottleneck. Plutonium-238 does not occur naturally. You cannot mine it. You have to make it inside a nuclear reactor by bombarding Neptunium-237 with neutrons. The process is slow, expensive, and requires reactors that are specifically configured for isotope production rather than power generation. During the Cold War, the United States produced plutonium-238 as a byproduct of its weapons program. When the weapons program scaled back in the 1990s, plutonium production stopped. NASA was left with a stockpile that was slowly decaying and no way to make more. For nearly 2 decades, the space agency rationed what it had. New Horizons launched in 2006 with an RTG that carried some of the last available plutonium from the old stockpile. The Curiosity rover, which landed on Mars in 2012, carried an RTG built with plutonium that had been carefully hoarded for years. By the early 2010s, NASA was projecting that it would run out of plutonium entirely by the 2020s unless production restarted. Production restarted. In 2013, the Department of Energy began producing small amounts of new plutonium-238 at Oak Ridge National Laboratory in Tennessee. The process is still slow, the output is still limited. As of 2024, the United States produces only a few hundred grams of plutonium-238 per year. That is enough for maybe one deep space mission every few years, if the mission is designed carefully and the RTGs are made as efficient as possible. It is not enough for a fleet of spacecraft. It is not enough for ambitious exploration of the outer solar system. It is barely enough to keep the lights on. The Europeans have their own plutonium problem. The European Space Agency has historically purchased plutonium-238 from Russia, which continued producing it long after the United States stopped. But after Russia's invasion of Ukraine in 2022, those purchases became politically untenable. Europe is now facing the same shortage NASA dealt with in the 2000s, and there is no easy solution. Building a plutonium production infrastructure takes years and costs hundreds of millions of dollars. It is not the kind of thing you can spin up quickly. China, meanwhile, has ramped up its own plutonium-238 production as part of its deep space exploration plans. The country has not published detailed numbers, but analysts believe China is now producing more plutonium-238 per year than the United States. If that is true, and if China continues investing in RTG development, it could become the dominant player in deep space exploration over the next few decades, simply because it will be the only country with enough fuel to power missions beyond Mars. This is the geopolitics of space exploration in the 21st century. Not rockets, not computers, plutonium. The country that controls the supply of this one specific isotope controls access to the outer solar system, and right now, no one has enough. Back on Voyager 2, the RTGs are still doing their job. The plutonium is still decaying. The thermocouples are still converting heat into electricity. But the output has dropped so far that the spacecraft is now running on a power budget smaller than a single laptop computer. Every watt matters. Every milliwatt matters. The mission team is down to counting the energy cost of individual commands sent from Earth, because even the act of receiving and processing a command draws power from the dwindling reserve. The thermocouples themselves are the unsung heroes here. These are not fancy devices. They are just junctions of two different metals, usually silicon-germanium alloys, arranged so that one end sits near the hot plutonium and the other end is exposed to the cold of space. When you create a temperature difference across certain materials, they generate a small voltage. String enough of these junctions together and you get usable power. The efficiency is terrible. RTGs convert only about 6 to 7% of the heat from plutonium decay into electricity. The rest is waste heat, radiated into space, but 6% is enough. It has been enough for 50 years. The problem is that those thermocouples wear out. The metal junctions degrade. The alloys diffuse into each other at the atomic level. The temperature gradient becomes less effective, and there is no way to replace them, no way to repair them, no way to reverse the damage. The RTGs on Voyager 2 are sealed units. They were sealed before launch. They will stay sealed until the spacecraft eventually collides with something millions of years from now, or until the heat death of the universe, whichever comes first. So the power drops 4 watts per year, every year, like clockwork. And the mission team watches the curve and knows exactly when the lights will go out. The current projection is that by the early 2030s, Voyager 2 will not have enough power to run a single science instrument. The exact date depends on a lot of variables: how efficiently the remaining systems operate, whether any unexpected failures force early shutdowns, whether NASA can find clever ways to reduce power consumption even further. But the window is closing. The math is clear. Somewhere between 2030 and 2035, the spacecraft will cross the threshold where it can no longer generate enough electricity to send a signal back to Earth. When that happens, Voyager 2 will still be intact. The RTGs will still be producing a little bit of heat, just not enough to power anything useful. The structure will still be flying through space at 9.6 miles per second. The golden record will still be mounted on the side, but the transmitter will be silent. The instruments will be offline. The spacecraft will become an artifact, a tombstone, a message in a bottle that no one will ever be able to open. And the people who built it, the engineers who spent their careers nursing it through 50 years of spaceflight, will have to let it go. There is something almost poetic about the fact that Voyager 2's death is tied directly to the decay of plutonium. The same nuclear process that gave the spacecraft life is the process that will end it. The mission was always on a countdown. The engineers knew that from day one. They just did not know how long the countdown would last. Turns out, it lasted longer than anyone expected. Longer than the design life, longer than the warranty, longer than most of the people who built it, but not forever. Nothing lasts forever, not even a machine designed to outlive its makers. The RTGs will keep producing heat for centuries. The Plutonium-238 has a half-life of 87.7 years, so even 100 years from now, the generators will still be warm, just not warm enough to matter, not warm enough to power anything, not warm enough to tell anyone they are still there. Voyager 2 will drift through interstellar space, carrying a heart that beats slower and slower and slower, until eventually it is beating so faintly that even the spacecraft itself cannot feel it anymore. And somewhere out there in the dark, beyond the reach of the sun, beyond the boundary where the solar wind fades into the interstellar medium, that heart will keep ticking, pointlessly, silently, alone. There is a line in space where the sun's voice stops and the galaxy's begins. For most of human history, we did not know that line existed. We assumed the sun's influence just faded gradually, the way a flashlight beam dims with distance until it blends into the dark. Turns out, the universe does not work that way. The boundary is real, it is sharp. And on November 5, 2018, a machine we built 41 years earlier crossed it and lived to tell us what was on the other side. Voyager 2 entered interstellar space that day. Not the interstellar space of science fiction, where starships jump between solar systems in the blink of an eye. The real thing. The cold, vast, indifferent medium that fills the gaps between stars. The place where our sun's protective bubble finally runs out of push, and the rest of the galaxy takes over. Voyager 2 became only the second human-made object ever to cross that threshold. Voyager 1 had done it 6 years earlier in 2012, but Voyager 1's plasma instrument had failed decades before it reached the boundary. It could detect the change indirectly through other measurements, but it could not taste the plasma itself. Voyager 2 could, and that made all the difference. NASA did not announce the crossing until December 10, more than a month after it happened. Not because they were being secretive, but because they needed time to analyze the data and make sure they were reading it correctly. You do not announce that humanity has left the solar system unless you are absolutely certain. The data had to be checked, cross-checked, debated and confirmed by multiple teams before anyone was willing to say the words out loud. When they finally did, the announcement was careful, precise and unambiguous. Voyager 2 had crossed the heliopause. It was no longer inside the heliosphere, it was in interstellar space. To understand what that means, you need to understand what the heliosphere actually is, because most people hear the word and picture something vaguely spherical, maybe a faint glowing shell around the solar system, like a soap bubble. The reality is stranger and far more violent. The heliosphere is not a structure, it is a collision, a continuous ongoing crash between two opposing forces. On one side, you have the solar wind, a relentless stream of charged particles, mostly protons and electrons, that the sun has been spewing into space for billions of years. The sun does not gently radiate light and warmth like a campfire. It screams. It hurls roughly 1 million tons of plasma into space every second, moving at speeds between 700,000 and 2 million miles per hour depending on the solar cycle. That wind rushes outward in all directions, filling the space around the sun with a hot, thin, magnetized bubble of particles that drowns out almost everything else. On the other side, you have the interstellar medium, the gas and dust and cosmic rays that drift through the galaxy between the stars. The interstellar medium is cold, dense by comparison, and it is moving. The entire local neighborhood of stars, including our sun, is drifting through the galaxy at roughly 50,000 miles per hour relative to the surrounding gas. So from the sun's perspective, the interstellar medium is not sitting still. It is slamming into the heliosphere like wind hitting the front of a moving car. The heliopause is where those two forces meet, and neither one wins. The solar wind pushes outward until it hits the interstellar medium and loses momentum. The interstellar medium pushes inward until it hits the solar wind and gets deflected. The result is a boundary layer, a thin turbulent region where the plasma from inside the heliosphere mixes with the plasma from outside, and the magnetic fields twist into knots, and the temperature and density shift dramatically over a span of just a few astronomical units. That boundary is not smooth and it is not stable. It ripples, it flexes. The solar wind varies with the sun's 11-year cycle, so the heliopause bulges outward during solar maximum and contracts inward during solar minimum. The interstellar medium is not uniform either. The local cloud of gas the sun is currently moving through has its own density variations, and when the sun drifts into a thicker patch, the heliopause gets pushed inward. The whole thing is dynamic, constantly shifting, more like the surface of the ocean than a fixed line on a map. Voyager 2 crossed that boundary at roughly 11 billion miles from Earth. That translates to about 120 astronomical units, more than 4 times the distance from the Sun to Neptune. The spacecraft had been flying for 41 years. It had visited Jupiter, Saturn, Uranus, and Neptune. It had spent decades crossing the outer reaches of the solar system, where sunlight is so faint that noon looks like deep twilight. And then, finally, it reached the edge. The crossing itself was not violent. There was no turbulence, no shockwave. Voyager 2 did not feel a thing. The spacecraft just kept flying at 9.6 miles per second, the same speed it had been traveling for years, and the environment around it changed. The plasma got colder, denser. The magnetic field rotated slightly. The flux of high-energy particles arriving from deep space, particles called galactic cosmic rays, suddenly jumped to levels higher than anything the spacecraft had measured before. And the solar wind, the hot, fast plasma that had surrounded Voyager 2 for its entire journey, vanished. That last part is what made the detection definitive. Voyager 2 carries an instrument called the Plasma Science Experiment, a device specifically designed to measure the speed, density, temperature, and composition of charged particles in space. It is a simple instrument by modern standards, just a set of detectors aimed in different directions to catch particles as they stream past the spacecraft. But it works, and it was still working in November 2018, which made Voyager 2 the only spacecraft ever to directly measure the plasma environment on both sides of the heliopause. On November 5, the Plasma Science Experiment stopped detecting solar wind. Not a gradual decline, not a slow fade. The signal dropped to 0. One day the instrument was measuring the hot, fast, low-density plasma characteristic of the solar wind. The next day it was measuring cold, slow, high-density plasma characteristic of the interstellar medium. The jump in density was dramatic. The plasma outside the heliosphere was denser by a factor of 20 compared to the plasma inside. That is not a subtle shift. That is a wall. At the same moment, 2 other instruments on Voyager 2 registered their own changes. The cosmic ray subsystem and the low-energy charged particle instrument both saw a sharp increase in the flux of galactic cosmic rays. These are high-energy particles, mostly protons, that have been accelerated to nearly the speed of light by supernova explosions and other violent events across the galaxy. Inside the heliosphere, the solar wind acts as a partial shield, deflecting and slowing down cosmic rays before they can penetrate deep into the solar system. That is one of the reasons life on Earth is possible. The heliosphere blocks a lot of the radiation that would otherwise sterilize the planet. But outside the heliosphere there is no shield. The cosmic rays hit Voyager 2 at full strength. The count rate jumped by roughly 40% in a single day and stayed high. Those two signals, the loss of solar wind and the spike in cosmic rays, were enough to confirm the crossing. But there was a third piece of data that made the result even more interesting. Voyager 2's magnetometer, the instrument that measures the strength and direction of magnetic fields in space, recorded a shift in the field orientation right around the time of the crossing. The magnetic field inside the heliosphere is tangled and chaotic, twisted by the sun's rotation and the turbulence of the solar wind. The magnetic field outside the heliosphere, in the local interstellar medium, is more organized. It runs in a consistent direction, shaped by the large-scale structure of the galaxy. When Voyager 2 crossed the heliopause, the magnetometer showed that the magnetic field just outside the boundary was oriented almost parallel to the magnetic field just inside. That was unexpected. Older models predicted that the interstellar magnetic field should be rotated significantly compared to the heliospheric field because the two regions are not supposed to be connected. But Voyager 1 had seen the same thing when it crossed in 2012. The fields were aligned. Voyager 2 confirmed it. Whatever process is happening at the heliopause, it is creating a smoother magnetic transition than anyone predicted. The fields on either side are talking to each other. They are coupled, and that changes how scientists think about the boundary itself. The findings also revealed something strange about the plasma just inside and just outside the heliopause. The solar wind plasma right before the crossing was denser than models predicted, not by a huge amount, but enough to be noticeable. And the interstellar plasma just after the crossing was slightly warmer than expected, though still much colder than the solar wind. The simplest explanation is that the boundary is not a clean break. There is a transition layer, a compressed region where the two plasmas mix and interact before fully separating. The heliopause is not a line, it is a zone, narrow, maybe only a few astronomical units thick, but real. A place where the solar system and the galaxy overlap. Don Gurnett, a physicist at the University of Iowa who has worked on the Voyager mission for decades, put it bluntly after the data came in: the old idea that the solar wind will just be gradually whittled away as you move away from the sun is simply not true. There is a boundary, a real, measurable, physical boundary. The heliosphere ends, and when you cross it, you know. Ed Stone, the Voyager project scientist who has been with the mission since before launch, described the moment with the kind of precision you would expect from someone who has spent 50 years analyzing spacecraft data. November 5 was the day that the galactic cosmic ray intensity abruptly increased and did not go back down. It was the day the plasma instrument quit measuring the solar wind. It was the day everything changed. Stone has been waiting for that moment since 1977. He knew it was coming. He just did not know when. And when it finally happened, the data was so clear that there was no room for doubt. The confirmation that Voyager 2 had crossed into interstellar space was a huge deal for one simple reason. Voyager 1 had done it first, but Voyager 1's plasma instrument had died in 1980, shortly after the Saturn flyby. For 32 years, that spacecraft flew blind to one of the most important measurements you can make in the outer solar system. It could still detect cosmic rays, it could still measure magnetic fields, but it could not taste the plasma. It could not directly confirm that the solar wind had disappeared. When Voyager 1 crossed the heliopause in 2012, scientists had to infer the crossing from indirect evidence. The cosmic ray spike was there, the magnetic field shift was there, but the smoking gun, the direct measurement of the plasma transition, was missing. Voyager 2 had that smoking gun. Its plasma science experiment was still working. And when the spacecraft crossed the heliopause 6 years after Voyager 1, It delivered the first direct measurement of the interstellar plasma that surrounds our solar system. That single data point answered questions that had been sitting unanswered since 2012. It confirmed that the boundary is real, that the plasma changes are sharp, and that Voyager 1's earlier crossing was not a fluke or a temporary fluctuation. The heliopause is consistent, it is reproducible. It behaves the way a physical boundary should behave. The two crossings also provided something else, a comparison. Voyager 1 crossed the heliopause at a distance of about 121 astronomical units from the Sun, in a completely different direction from Voyager 2. The two spacecraft are flying away from the solar system on opposite sides, separated by billions of miles. The fact that they both detected similar boundary conditions at roughly similar distances tells scientists that the heliosphere is, on average, fairly symmetric. It is not wildly lopsided. It is not shaped like a comet with a long tail stretching behind the Sun. It is more or less a bubble, compressed slightly in the direction the Sun is moving through the galaxy, but still recognizably round. That was not obvious before Voyager. Some models predicted that the heliosphere would be drastically elongated, stretched into a teardrop shape by the motion of the Sun through the interstellar medium, with a tail extending hundreds of astronomical units downstream. Voyager's measurements suggest that is not the case. The heliosphere is more compact than those models predicted. The boundary sits at roughly 120 astronomical units in all directions, give or take. That has implications for how we think about the interaction between the Sun and the galaxy. The Sun is not passively drifting through space. It is actively carving out a cavity, a region of space where its influence dominates, and that cavity has a well-defined edge. The data also gave scientists their first real look at the local interstellar medium, the cloud of gas and dust that our solar system is currently passing through. Astronomers have studied the interstellar medium for decades, using telescopes that observe distant stars and measure how their light is absorbed by intervening gas. But those observations are always looking at material that is light years away. Voyager 2 was sitting in the local interstellar medium, measuring it directly from the inside. The density Voyager 2 recorded, roughly 0.002 particles per cubic centimeter, matched the predictions astronomers had made based on remote observations. That agreement is a big deal. It means the models work. It means our understanding of the local galactic environment is more or less correct. And it means the next time we send a spacecraft into interstellar space, we will have a much better idea of what it is going to encounter. The magnetic field alignment between the heliosphere and the local interstellar medium is still puzzling scientists. The fact that the fields are nearly parallel suggests that there is some kind of connection between the two regions, some process at the boundary that is smoothing out what should be a more chaotic transition. One possibility is magnetic reconnection, a phenomenon where magnetic field lines from two different regions break apart and reconnect in a new configuration, releasing energy in the process. Magnetic reconnection happens all the time in the Sun's atmosphere. It is what drives solar flares and coronal mass ejections. If the same process is happening at the heliopause, it could be stitching together the heliospheric and interstellar magnetic fields, creating a smoother transition than a simple collision would allow. Another possibility is that the interstellar magnetic field itself is being shaped by the heliosphere. The solar wind is not just pushing against the interstellar medium, it is also dragging the interstellar magnetic field along with it, wrapping the field lines around the outside of the heliosphere like cloth draped over a ball. If that is happening, the magnetic field just outside the heliopause would naturally align with the field just inside because they are connected at a deeper level. The boundary would still be real, but the magnetic fields would be linked across it. Sorting out which explanation is correct will take more data, and more data is not coming anytime soon. Voyager 2 crossed the heliopause in 2018 and kept going. It is not coming back. It is not circling around for another pass. The spacecraft is flying deeper into interstellar space every second, and the heliopause is now more than 1 billion miles behind it. Any follow-up observations will have to come from future missions, and there are no future missions currently on the books. NASA has proposals for an interstellar probe, a spacecraft specifically designed to fly out to the heliopause and study the boundary in detail. But that mission is still in the planning stages. If it gets funded, it will not launch until the 2030s at the earliest, and it will not reach the heliopause until the 2050s. By then, Voyager 2 will have been silent for decades. The crossing itself was also a reminder of just how far these spacecraft have traveled. 11 billion miles. That number is almost meaningless to a human brain. Our entire planet is only about 25,000 miles around the equator. You could drive around the Earth 500 times and still not cover the distance Voyager 2 has flown. Light, the fastest thing in the universe, takes more than 17 hours to travel from Voyager 2 back to Earth. When Mission Control sends a command to the spacecraft, it takes 17 hours for that command to arrive. If the spacecraft responds immediately, the response takes another 17 hours to get back. 34 hours round trip. A day and a half of waiting just to confirm that a command was received. That is the communication lag you are working with when you operate a spacecraft in interstellar space. You do not have conversations. You send instructions and hope for the best. The fact that Voyager 2 detected the heliopause crossing so clearly is also a testament to the quality of the instruments. These are devices built in the 1970s using technology from the Apollo era, vacuum tubes, analog circuits. Data storage measured in kilobytes, not gigabytes, and yet they worked. They worked well enough to detect a change in plasma density by a factor of 20, well enough to measure a 40% jump in cosmic ray intensity, well enough to track subtle shifts in magnetic field orientation across a boundary that is only a few astronomical units thick. The engineers who designed those instruments had no idea what the spacecraft would encounter in interstellar space. They just built them to be as sensitive and as robust as possible, and 50 years later, the instruments are still returning data that is changing our understanding of the galaxy. There is one more detail that makes Voyager 2's crossing significant, and it is easy to miss if you are not paying attention. The spacecraft did not just cross into interstellar space, it crossed into a specific part of interstellar space, a region that astronomers call the local interstellar cloud, a relatively dense clump of gas and dust that our solar system has been moving through for the last several thousand years. Before that, the Sun was in a different cloud, and before that, a different one. The galaxy is not uniform. It is filled with clouds and voids and streams of gas left over from ancient supernovae. The local interstellar cloud is just one of many, and we are passing through it at 50,000 miles per hour. In about 10,000 years, we will exit this cloud and enter a different region of space with different density, different temperature, different magnetic field strength. And when that happens, the heliopause will shift. It will move inward or outward depending on the pressure from the new environment. The boundary is not fixed. It moves with us as we drift through the galaxy. Voyager 2's measurements gave us a snapshot of the heliopause as it exists right now, in this specific moment in cosmic history, in this specific location in the galaxy. Future generations of humans, if they are still around in 10,000 years, will be living in a solar system with a different shaped heliosphere, a different boundary, a different relationship with the interstellar medium. The data Voyager 2 collected is not just a record of what the boundary looks like today. It is a record of what the boundary looked like in the early 21st century when humanity first reached interstellar space. That record will never be repeated. The local interstellar cloud will have moved on. The sun will be somewhere else. The conditions Voyager 2 measured will be gone, and Voyager 2 will still be out there, flying deeper into the dark, carrying the memory of the moment it crossed the line. The spacecraft is now more than 12.5 billion miles from Earth. It is moving at roughly 35,000 miles per hour relative to the Sun. It is no longer protected by the heliosphere. It is fully exposed to the interstellar medium, to the cosmic rays, to the magnetic fields, to the thin, cold plasma that fills the space between stars, and it is running out of time. The plutonium that powers its systems is decaying. The instruments are being shut down one by one. The transmitter is getting weaker. Within the next decade, Voyager 2 will no longer have enough power to send a signal back to Earth. And when that happens, the most distant human-made object in interstellar space will fall silent, leaving behind only the data it collected and the memory of the machines that listened. 15 billion miles is not a distance the human brain can process. You can say the number, you can write it down, you can even do the math and calculate how many times you could wrap that distance around the Earth. But you cannot feel it, you cannot picture it. The gap between where Voyager 2 is right now and the planet that built it is so vast that even light, the fastest thing in the universe, takes more than 18 hours to cross it one way. 37 hours round trip if you are waiting for a response. That is a day and a half. You send a message on Monday morning, and if everything works perfectly, you get an answer back Tuesday night. That delay is not a technical problem NASA can solve. It is a law of physics, and it is the backdrop against which every decision about Voyager 2's final years is being made. Because when you are operating a spacecraft at that distance, you do not get to troubleshoot in real time. You do not get to try something, see if it works, and adjust on the fly. You send a command and you wait. You wait 17 hours for the command to arrive. You wait for the spacecraft to execute it. You wait another 17 hours for the confirmation to come back. And if something goes wrong, if the command does not work the way you expected, you start the whole process over again. By the time you know you made a mistake, 37 hours have passed, and the spacecraft has been doing the wrong thing for more than a day. That is the environment NASA is working in as Voyager 2 enters the final stretch of its mission. And it is the reason every power management decision, every instrument shutdown, every command sent to the spacecraft is planned with the kind of precision you would expect from surgeons operating on a patient they can only see through a telescope. There is no room for error, no chance to walk anything back. Once an instrument is turned off, it stays off. The power budget does not allow for second guessing. NASA has known for years that this moment was coming. The plutonium powering Voyager 2's radioisotope thermoelectric generators has been decaying since the day the spacecraft launched in 1977. The power output has been dropping by about 4 watts per year every year like clockwork. In the beginning, 470 watts was more than enough to run every system on the spacecraft with power to spare. By the early 2000s, the margins had tightened. By the 2010s, NASA was already making cuts. And now, in the mid-2020s, the spacecraft is running on fumes. The engineers are down to the hard choices, the brutal ones. The choices that mean shutting down instruments that are still working, that are still returning valuable data, simply because there is not enough electricity left to keep them running. This is not a sudden crisis. It is a managed decline, a carefully choreographed farewell. NASA has a plan. They call it the phased shutdown approach. One instrument at a time, one system at a time. Prioritize the most scientifically valuable measurements and keep those running as long as possible. Sacrifice everything else. The goal is to stretch the mission lifetime as far as the physics will allow, squeezing every last bit of data out of Voyager 2 before the power runs out completely and the spacecraft goes silent forever. The current projection is that Voyager 2 will not have enough power to support even a single science instrument by sometime around 2030. Maybe 2032, maybe earlier if something unexpected fails. After that, the spacecraft might have enough juice to keep its transmitter running for a few more years, sending back a faint carrier signal that tells Earth it is still alive but has nothing left to say. And then, around 2036, even that will stop. The Deep Space Network will point its massive antennas at the coordinates where Voyager 2 is supposed to be, and they will hear nothing. Static. The background hiss of the galaxy, and Voyager 2 will still be out there, still flying, still obeying the laws of motion, but no longer able to tell anyone it exists. The first major shutdown happened in October 2024. NASA turned off the plasma science instrument. This was the same instrument that had delivered the smoking gun proof of Voyager 2's entry into interstellar space back in 2018. It had measured the sudden disappearance of the solar wind. It had recorded the jump in plasma density as the spacecraft crossed the heliopause. It was one of the key instruments for understanding the boundary between the solar system and the galaxy. And it was still working, still returning data, still doing its job. But it drew power, and there was not enough power left to run everything. So NASA shut it down. The decision was not made lightly. The plasma science instrument was one of the defining features of Voyager 2's mission. Voyager 1 had lost its plasma instrument back in 1980, shortly after the Saturn flyby, which meant Voyager 1 could not directly measure the plasma transition when it crossed the heliopause in 2012. Voyager 2 was the only spacecraft ever to make that measurement. It was the only machine in human history to taste the interstellar medium directly and tell us what it found. And now, 6 years after that historic crossing, the instrument was being turned off. Not because it failed, not because it stopped working, because the power budget could not support it anymore. Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, has been with the mission for decades. She has watched these spacecraft outlive their design life, outlive entire generations of engineers, outlive the Cold War that funded their construction, and she has been the one making the calls about what stays on and what gets turned off. In interviews, she has described the process as heartbreaking. These are instruments that have been running for nearly 50 years. Some of them are older than the people operating them. Shutting them down feels like saying goodbye to a friend you know you will never see again. But the alternative is worse. If NASA does nothing, if they let the power drain without making cuts, the spacecraft will simply die sooner. All the instruments will fail at once when the voltage drops below the threshold needed to keep the electronics functioning. The mission will end abruptly, chaotically, with no chance to prioritize or preserve the most important data streams. The phased shutdown approach is about control, about making sure the mission ends on humanity's terms, not the universe's, about squeezing every last bit of science out of Voyager 2 before the lights go out for good. The next instrument scheduled for shutdown is the low-energy charged particle detector. That one is expected to be turned off sometime in 2025. It measures particles with energies in the range of tens of kiloelectron volts to a few million electron volts, tracking the flow of ions and electrons in the space around the spacecraft. It has been running since launch. It has mapped the radiation environments of Jupiter, Saturn, Uranus, and Neptune. It has tracked the transition from the heliosphere to the interstellar medium. And now it is going to be turned off because the power budget cannot support it anymore. After that, the cosmic ray subsystem is on the chopping block. That shutdown is expected around 2026. The cosmic ray subsystem measures high-energy particles, the kind accelerated by supernova explosions and other violent events across the galaxy. It has been tracking the flux of galactic cosmic rays since Voyager 2 entered interstellar space, providing data that no other spacecraft has ever collected. The measurements show how cosmic ray intensity changes with distance from the heliopause, how the interstellar medium shields or channels those particles, and how the local galactic environment affects the radiation environment our solar system is drifting through. That data is irreplaceable, and in 2026, unless something changes, it will stop arriving. Each shutdown buys the mission a little more time. Each instrument that gets turned off reduces the spacecraft's power draw by a few watts, which means the remaining systems can keep running a little longer. The math is brutal but straightforward. Turn off the plasma science instrument and you save maybe 6 watts. Turn off the low-energy charged particle detector and you save another 4. Turn off the cosmic ray subsystem and you save 3 more. That is 13 watts total. At the current rate of power decay, 13 watts buys you maybe 3 years. 3 more years of keeping the spacecraft alive. 3 more years of data from the instruments that are still running. 3 more years before the next round of cuts. By the late 2020s, NASA will be down to the absolute essentials. The transmitter, which uses about 23 watts to send data back to Earth. The computers, which use another 20 watts to process commands and manage the spacecraft's systems. The attitude control thrusters, which fire occasionally to keep the spacecraft's antenna pointed at Earth. And maybe 1 or 2 science instruments, chosen because they provide the most unique data or because their measurements cannot be replicated by any other spacecraft. Everything else will be off. The heaters will be off. The backup systems will be off. Parts of the spacecraft will be colder than they were ever designed to operate. The engineers will be hoping that the electronics keep working anyway, that the temperature tolerance margins built into the components back in the 1970s are conservative enough to handle conditions the designers never anticipated. This is not the way anyone wanted the mission to end. The people who built Voyager 2 assumed the spacecraft would last maybe 5 years, 10 if they got lucky. The grand tour of the outer planets was supposed to be the whole mission. Visit Jupiter, visit Saturn, visit Uranus and Neptune if the trajectory worked out, and then the spacecraft would drift into the outer solar system and eventually stop transmitting because the power ran out. That was the plan. The fact that Voyager 2 is still operating nearly 50 years later, still returning data from interstellar space, is a testament to the quality of the engineering. But it is also a slow-motion goodbye that no one knows how to process because the spacecraft is still working. It is still doing its job, and the people who have spent their careers keeping it alive are watching it die one instrument at a time, knowing there is nothing they can do to stop it. Operating a spacecraft at 15 billion miles is technically absurd. The signal Voyager 2 transmits is 23 watts. That is less power than a refrigerator light bulb. By the time that signal crosses 15 billion miles, it has spread out so thin that the power density reaching Earth is measured in billionths of a watt. NASA listens for that whisper using the Deep Space Network, a collection of massive radio antennas scattered across 3 continents. The antennas are 70 meters in diameter. Picture a satellite dish the size of a football field. That is what it takes to hear Voyager 2 from interstellar space. And even with antennas that large, the signal is right at the edge of detectability. The engineers have to filter out noise from the Earth's atmosphere, noise from the sun, noise from distant radio sources scattered across the galaxy. They have to lock onto a carrier signal so faint that it would be drowned out by a cell phone transmitting from Jupiter. The Deep Space Network is the only reason Voyager 2 is still a functional mission. Without it, the spacecraft would still be out there, still transmitting, but no one on Earth would be able to hear it. The DSN consists of 3 major antenna complexes, one near Goldstone, California, one near Madrid, Spain, one near Canberra, Australia. The locations are spread evenly around the planet, so that no matter where Earth is in its rotation, at least one of the antennas has a line of sight to Voyager 2. The spacecraft never sets, it never dips below the horizon. As long as one of the 3 stations is pointed in the right direction, NASA can maintain contact. But even the Deep Space Network has limits. The 70-meter antennas are the largest dishes in the network, and they are booked solid. NASA uses them to communicate with dozens of spacecraft scattered across the solar system. The Mars rovers, the Juno probe at Jupiter, the Perseverance rover, the Curiosity rover, the New Horizons spacecraft, which is flying through the Kuiper Belt. All of them need time on the antennas. All of them are competing for the same limited resource. Voyager 2 gets a few hours of tracking time per week. That is it. The rest of the time, the antennas are pointed somewhere else, talking to some other mission. And as the power on Voyager 2 continues to drop, the signal will get weaker. At some point, the spacecraft's transmissions will fall below the noise floor. The DSN will still be listening, but it will not be able to pick out Voyager 2's signal from the background static. When that happens, contact will be lost, not because the spacecraft stopped transmitting, but because Earth stopped being able to hear it. That threshold is expected to hit around 2036, give or take a few years depending on how efficiently the remaining systems can be managed. By then, Voyager 2 will be even further from Earth. The signal will have weakened even more, and the Deep Space Network, as sensitive as it is, will not be able to bridge the gap. The spacecraft will still be there, it will still be flying, but it will be alone, unreachable. A message in a bottle, drifting through the galaxy with no way to tell anyone what it has seen. The antenna pointing incident in 2023 was a preview of just how fragile this whole operation is. In late July of that year, NASA sent a routine command to Voyager 2 as part of a planned series of operations. Someone made a mistake. The command sequence accidentally included an instruction that tilted the spacecraft's antenna 2 degrees away from Earth. 2 degrees. That is roughly the width of your thumb held at arm's length. It does not sound like much. At 15 billion miles, it is everything. Voyager 2 went silent. NASA heard nothing. The spacecraft was still there. It was still flying. It was still transmitting. But the signal was no longer aimed at Earth. It was spraying out into empty space in a direction where no one was listening. For 2 weeks, the engineers at the Jet Propulsion Laboratory scrambled. They recalculated the spacecraft's position. They adjusted the pointing of the Deep Space Network antennas, trying to pick up any stray signal that might have scattered in Earth's direction. And on August 1, they found something. A faint carrier signal. Too weak to contain any real data, but strong enough to confirm that Voyager 2 was still alive, still operating, still transmitting. That detection buoyed spirits, as Suzanne Dodd later put it, because it meant the spacecraft had not failed, it had not been hit by a micrometeorite, it had not tumbled out of control. It was simply pointing the wrong way, and if it was still functioning, there was a chance NASA could fix it. The problem was distance. Voyager 2 was so far away that any command sent from Earth took 18.5 hours to reach the spacecraft. The response, if it worked, would take another 18.5 hours to travel back, 37 hours round trip. If the engineers sent the wrong command, they would not know for more than a day and a half, and by then it might be too late to correct. They had one shot. On August 4, NASA sent the command. It was a simple instruction: reorient your antenna, point it back at Earth. The command traveled outward at the speed of light, crossing the orbits of the planets, crossing the heliopause, crossing 12.5 billion miles of interstellar space. 18.5 hours later, it arrived. Voyager 2 received the instruction. Its thrusters fired. The spacecraft rotated by 2 degrees, and 18.5 hours after that, the signal came back. Full contact restored. The spacecraft was talking again, but the scare was real, because that 2-week silence was a glimpse of what is coming. Someday soon, Voyager 2 will stop transmitting, not because of a mistake, but because it has run out of power. And when that happens, there will be no command that can bring it back. The silence will be permanent. The engineers who work on Voyager 2 have a strange relationship with the spacecraft. Most of them were not alive when it launched. They inherited the mission from the generation that built it. They learned the systems, studied the schematics, debugged the software, and took over the job of keeping a 50-year-old machine alive. And now they are the ones watching it die. They are the ones making the decisions about which instruments to turn off, which systems to sacrifice, which pieces of the spacecraft to let go cold. And they are doing it knowing that every choice they make is a choice about how the mission ends, about what humanity's last words from interstellar space will be. Calla Cofield, a spokesperson for NASA's Jet Propulsion Laboratory, described the communication pause in 2023 as a reminder of just how far Voyager 2 has traveled and how precarious the connection is. The spacecraft is operating in an environment it was never designed for. It has been flying for nearly 5 decades. Its components are older than the people operating them. The fact that it is still working at all is borderline miraculous. And the fact that NASA can still communicate with it, can still send commands and receive data across 15 billion miles of empty space, is a tribute to the engineers who have spent their careers nursing it through the dark. But those engineers also know the clock is running. They know the power budget. They know the decay curve. They know that sometime in the next decade, Voyager 2 will cross the threshold where it can no longer generate enough electricity to send a signal back to Earth. And they are doing everything they can to delay that moment, to stretch the mission as far as it will go, to make sure that when Voyager 2 finally goes silent, it does so having given humanity every bit of data it was capable of collecting. The phased shutdown is not just a technical strategy, it is an emotional process, a way of saying goodbye slowly, one instrument at a time. Each shutdown is a small funeral, a recognition that this piece of the spacecraft, this system that has been working faithfully for decades, is being turned off for the last time, and there is no bringing it back, no repair mission. No software patch that can restore what has been lost. Once an instrument is shut down, it stays off. The mission moves forward without it. The people who work on Voyager have described the experience as surreal. They spend their days sending commands to a machine that is 15 billion miles away, knowing that every command they send could be the last one that works. They monitor the telemetry, track the power levels, calculate the remaining mission lifetime down to the month. And they do it all while knowing that the end is coming, not because the spacecraft failed, But because the universe is large and power is finite, and even the best machines eventually run out of time, there is also a practical side to the shutdowns that does not get talked about as much. Turning off instruments reduces the data rate. Less data means less load on the transmitter. Less load on the transmitter means the signal can be detected more easily by the deep space network. It also means the spacecraft can use a lower power mode, conserving energy that can be redirected to other systems. The engineers are optimizing, they are making trade-offs. They are balancing scientific return against mission longevity, trying to find the sweet spot where Voyager 2 can keep transmitting useful data for as long as possible without burning through the power budget so fast that the mission ends prematurely. That optimization is happening in real time. Every few months, the mission team reviews the spacecraft's status. They look at the power levels. They look at the health of the remaining instruments. They run projections, and then they decide whether any additional systems need to be shut down to keep the mission alive a little longer. It is a continuous process, a rolling negotiation with physics, and the engineers are losing, not because they made mistakes, but because the second law of thermodynamics does not care how clever you are. Entropy always wins. By the early 2030s, the decisions will get even harder. NASA will be down to the absolute minimum systems needed to keep the spacecraft functioning. The transmitter, the computers, the attitude control thrusters, maybe one science instrument if they can stretch the power budget far enough. And at that point, the mission will no longer be about collecting data. It will be about keeping the connection alive, about making sure that when Voyager 2 finally goes silent, humanity has had the chance to say a proper goodbye. The timeline is not set in stone. A lot depends on variables NASA cannot fully control: how efficiently the remaining systems operate, whether any components fail unexpectedly, whether the thermocouples in the radioisotope thermoelectric generators degrade faster or slower than predicted. But the broad strokes are clear. By 2030, Voyager 2 will not have enough power to run any science instruments. By 2036, the signal will be too weak for the deep space network to detect. And after that, silence, permanent, irreversible. The spacecraft will still be there, still flying, still carrying the golden record, still obeying the laws of motion as it drifts deeper into the galaxy. But Earth will no longer be able to hear it, and it will no longer be able to hear Earth. That is the future NASA is planning for. A future where the most distant human-made object in the universe becomes unreachable, where the machine that traveled further than any other, that visited more planets than any other, that sent back more data than any other, finally falls silent and disappears into the dark. Not because it failed, but because it succeeded so completely that it flew beyond the point where we could follow. And somewhere on that spacecraft, bolted to the side, protected by an aluminium case, there is a golden record, a 12-inch disc etched with sounds and images from Earth, greetings in 55 languages, music from Beethoven, Chuck Berry, and traditional folk songs from cultures around the world. Diagrams showing where Earth is located relative to nearby pulsars. Instructions on how to play the record, assuming whoever finds it has figured out how to build a turntable from scratch. The record is humanity's message to the galaxy. A statement about who we are, what we made, what we loved. And it is still there, still intact, still waiting for someone to find it. Even after the power runs out, even after the transmitter goes silent, even after every person who worked on the mission has died, the record will still be there, Voyager 2's final gift to the universe, a message that will outlast the civilization that sent it. There is a disc bolted to the side of Voyager 2, 12 inches across, gold-plated, spinning through interstellar space at 35,000 miles per hour. It has been traveling for nearly 50 years. It will keep traveling for millions more. And if someone ever finds it, if some intelligence somewhere in the galaxy ever intercepts this tiny metal artifact drifting through the dark, they will discover something strange, a record, not a digital file, not a hologram, not some futuristic storage medium we have not invented yet, an actual phonograph record, the kind you play on a turntable with a needle. The golden record is humanity's most ambitious message in a bottle, and it is also one of the most absurd, because the odds of anyone ever finding it are so close to zero that they might as well be zero. Space is unimaginably vast. Voyager 2 is unimaginably small. The spacecraft is not aimed at any particular star. It is not following a trajectory that will bring it close to another solar system anytime soon. At its current speed, it would take more than 70,000 years just to reach the nearest star, and it is not even headed in that direction. It is flying sideways through the galaxy, drifting through the space between stars, covering distance that sounds impressive by human standards, but is barely a rounding error on the scale of the Milky Way. And yet we sent the record anyway. We etched sounds and images and music into a metal disc, sealed it in an aluminium case, and bolted it to the side of a machine we knew would eventually go silent and disappear into the void. We did it knowing no one would probably ever hear it. We did it because the act of sending it mattered, because we wanted to believe that even if the message is never received, the fact that we tried to send it says something about who we are. The golden record was Carl Sagan's idea. Not his alone, but he was the driving force behind it. Sagan was an astronomer, a cosmologist, a science communicator, and a man who believed deeply in the possibility of life beyond Earth. He had spent years thinking about how humanity might communicate with an alien intelligence if we ever got the chance. What would we say? How would we say it? What could we possibly include in a message that would make sense to a species that evolved on a different planet, under a different star, with no shared language, no shared biology, no shared frame of reference? The Voyager mission gave him a chance to try. In 1977, NASA was preparing to launch 2 spacecraft on a grand tour of the outer planets. Voyager 1 and Voyager 2 would visit Jupiter, Saturn, Uranus, and Neptune, and then keep going. They would leave the solar system entirely, flying out into interstellar space where no human-made object had ever been. And they would keep flying for millions of years, long after their power ran out, long after contact with Earth was lost. Sagan saw an opportunity. If these spacecraft were going to be wandering the galaxy for eons, why not send a message along with them? A greeting, a snapshot of Earth, a way of saying to the universe, we were here, and this is what we made. NASA agreed. They gave Sagan and his team at Cornell University a budget and a deadline. The spacecraft were launching in a matter of months. Whatever message they were going to send had to be designed, built, tested, and installed on both Voyagers before the launch window closed. Sagan assembled a team: scientists, engineers, artists, linguists, musicians. They had one job: figure out how to communicate the essence of humanity to an audience that might not exist, using a medium that might not make sense, and do it in a way that could survive millions of years of radiation, cosmic rays, and micrometeorite impacts without degrading into noise. The result was a 12-inch gold-plated copper disc, encoded with analog audio and images, packaged with a cartridge, a needle, and a set of instructions etched directly onto the surface of the record's protective cover. The instructions are written in symbols, diagrams showing how to play the record, how fast to spin it, how to decode the images. There is a map showing Earth's location relative to 14 pulsars, rapidly spinning neutron stars that emit radio pulses at precise intervals. The map uses the pulsars as reference points, the way sailors used to navigate by the stars. If someone finds the record and figures out the pulsar map, they can trace the origin of the message back to a specific point in the galaxy at a specific moment in time. Assuming they understand the concept of pulsars, assuming they have the technology to measure pulsar periods, assuming they care, the contents of the Golden Record are divided into 3 sections: sounds, images, and music. The sounds section contains 116 recordings of natural and human-made noises from Earth: wind, thunder, rain, surf, crickets, frogs, birds, whales, a crying baby, a heartbeat, footsteps, laughter, a kiss, the sound of a train, a car, a horse and cart, a rocket launch, a blacksmith hammering metal, a saw cutting wood, Morse code, the beep of a pulsar, a human voice saying hello in 55 different languages, from ancient Sumerian to modern Mandarin. The goal was to capture the acoustic texture of life on Earth, to give whoever found the record a sense of what it sounds like to be here, to be alive, to be human. The images section contains 118 photographs and diagrams encoded as audio signals using a system similar to analog television. Each image is a series of audio tones that, when decoded properly, will produce a picture. The images include mathematical definitions, a diagram of DNA, illustrations of human anatomy, pictures of landscapes, oceans, mountains, cities. There are images of people from different cultures around the world, a family eating dinner, a woman nursing a child, a man building a house, athletes running, dancers dancing, children playing. The goal was to show the diversity of human life, to show that we are not one thing, that we come in many forms, live in many ways, occupy many different environments. The music section is the longest, 90 minutes of recordings from cultures around the world: Bach, Beethoven, Mozart, Stravinsky, Chuck Berry, Louis Armstrong. Traditional folk songs from Peru, Japan, Senegal, India, China, a Navajo chant, an Australian Aboriginal song, panpipes from the Solomon Islands, a Bulgarian folk tune. The goal was not to create a greatest hits album. The goal was to show range, to show that humans make music, that we have been making music for thousands of years, that music is a universal part of the human experience, even though the specific sounds vary wildly from culture to culture. Choosing what to include was agonizing. The team had 90 minutes of space on the record, 90 minutes to represent the entire history of human culture, human achievement, human emotion. What do you leave out? What do you prioritize? Do you include more science and less art, more music and fewer images? Do you focus on the things that make us unique or the things that make us universal? Every choice was a compromise. Every inclusion meant something else had to be excluded, and no matter what they chose, the record would be incomplete. A snapshot, a fragment, a tiny slice of what it means to be human, frozen in time, sent into the void with the hope that someone, somewhere, might find it and understand. The team debated endlessly. Should they include recordings of war, of suffering? Should they show the darker side of humanity, or only the best parts? Sagan argued for honesty. He wanted to include images of poverty, conflict, the realities of life on Earth. Others argued that this was humanity's introduction to the galaxy. It should be aspirational. It should show what we are capable of at our best, not what we have done at our worst. In the end, they compromised. The record is mostly positive. There are no images of war, no recordings of violence. The message is optimistic, hopeful, carefully curated to present humanity as a species worth knowing. Whether that is honest or not is a different question. There is also the problem of context. The golden record assumes that whoever finds it will be able to decode it, that they will recognize the diagrams as instructions, that they will understand the concept of a phonograph, that they will have the technology to convert analog audio signals into images. Those are not small assumptions. We are asking an unknown intelligence with an unknown evolutionary history, an unknown sensory system, an unknown understanding of physics, to figure out a technology that humans invented in the late 19th century and mostly abandoned by the early 21st. We are handing them a piece of obsolete hardware and hoping they can reverse engineer it. Carl Sagan was aware of the problem. He and his team included as much information as they could on the record's cover, instructions, diagrams, reference points, but there is only so much you can explain with pictures. At some point, you have to assume a baseline level of intelligence and curiosity. You have to assume that if someone finds the record, they will be smart enough to figure it out, or at least curious enough to try. And if they are not, if they find the record and toss it aside as meaningless debris, well, at least we tried. The absurdity of the whole project is part of what makes it so human. We built a message for an audience that probably does not exist, using a format they probably would not understand, and sent it on a trajectory that probably will not bring it anywhere near another civilization for millions of years. And we did it anyway, because we wanted to. Because the act of reaching out, of trying to connect, of sending a greeting into the void, matters to us even if no one is listening. That impulse, that need to be known, to leave a mark, to say we were here, is one of the most fundamental parts of being human. And the golden record is the purest expression of that impulse we have ever created. There is something deeply moving about the fact that the record exists at all. Not because it is likely to be found, but because it represents a version of humanity that is worth celebrating. The record does not include stock prices. It does not include political arguments. It does not include advertisements or propaganda or any of the noise that fills so much of modern life. It includes music, laughter, the sound of a mother and child, the image of a family sharing a meal. It includes the things that matter, the things that make life worth living, and it sends those things into the galaxy as a statement about who we are at our best. The fact that the record was created in 1977, at the height of the Cold War, makes it even more remarkable. The United States and the Soviet Union were locked in a nuclear standoff that could have ended human civilization at any moment. The world was divided by ideology, by politics, by fear, and yet the golden record includes greetings in Russian. It includes music from the Eastern Bloc. It includes images of people from every corner of the planet, presented not as enemies or competitors, but as members of a single species. The record is a statement that transcends politics. It is a message from humanity, not from one nation or one culture. And that message is simple. We are here. We made this. We hope you find it. We hope you understand. The selection of music was one of the most contentious parts of the project. Sagan wanted to include the Beatles. He wanted to include Here Comes the Sun because he thought it perfectly captured the optimism and beauty of the human experience. The Beatles agreed. The record label did not. They refused to grant the rights. So the most popular band in human history, the band that defined a generation, is not on the golden record. Instead, Chuck Berry is there. Johnny B. Good made the cut. Rock and roll is represented. But the Beatles are not. That decision still frustrates people who worked on the project. It is a reminder that even when you are trying to send a message to the stars, you still have to deal with lawyers and copyright law. The images are equally revealing. There are pictures of cities, but not crowded, polluted, chaotic cities. The urban images are clean, organized, aspirational. There are pictures of technology, but not weapons. The record includes a diagram of a rocket, but not a missile. It includes images of construction, agriculture, art, but not destruction. The curation is obvious. The record is not lying about what humanity is. It is just being selective. It is showing the parts of ourselves we are proud of, and quietly leaving out the parts we are not. The greetings in 55 languages are some of the most fascinating content on the record. Each greeting is short, just a sentence or two. They range from the formal to the casual. The English greeting spoken by a young boy is simple. Hello from the children of planet Earth. The French greeting is warmer. Hello everybody. The Mandarin greeting is respectful. Hope everyone is well. We are thinking about you all. Please come here to visit when you have time. The greetings are not translations of each other. They are individual messages, each reflecting the culture and personality of the speaker. Some are poetic, some are direct, some are hopeful, some are wistful. Together they create a chorus of voices, all saying the same thing in different ways. We are here, we see you, we want to know you. There is also a message from Kurt Waldheim, the Secretary General of the United Nations in 1977. His message is formal, diplomatic, carefully worded. We step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate. It is a nice sentiment. It is also ironic, given that Waldheim was later revealed to have been a member of Nazi organizations during World War II. His presence on the Golden Record is a reminder that history is messy, that the people who create these messages are flawed, that even our most idealistic gestures carry the baggage of who we actually are. The Golden Record is not just a message, it is also a time capsule. Everything on it reflects 1977. The images, the music, the technology, the geopolitical context. If someone finds the record 1,000,000 years from now, they will not be learning about 21st century humanity. They will be learning about humanity as it existed in the late 1970s, during the Cold War, during the space age, during a brief moment when we believed we were on the verge of exploring the galaxy. The record is a snapshot, a freeze frame, a single moment in time preserved in metal and sent into the void. The case itself is designed to last. The aluminum cover is etched with the instructions, the pulsar map, and a diagram showing the location of Earth within the solar system. The gold plating on the disc protects the grooves from degradation. The whole thing is built to survive radiation, temperature extremes, and the occasional impact from dust particles traveling at interstellar speeds. NASA estimates the record could last 1 billion years or more before the data becomes unreadable. By that time, the Sun will be a red giant. Earth will be uninhabitable. The human species, if it still exists, will be unrecognizable. And Voyager 2 will still be out there, carrying a message from a planet that no longer exists. That is the paradox at the heart of the Golden Record. It was designed to communicate with an alien intelligence, but the more time passes, the more it becomes a message from us to ourselves. A reminder that we once existed, that we built things, that we cared enough to send a greeting into the universe even though we knew no one would probably hear it. The record is not really for aliens, it is for us. It is a statement about hope, about curiosity, about the refusal to accept that we are alone in the universe, even when every bit of evidence suggests we might be. The no one listening paradox is baked into the project. The Milky Way contains somewhere between 100 billion and 400 billion stars. Many of those stars have planets. Some of those planets are probably in the habitable zone, the region where liquid water could exist. Some of those planets might have life. Some of that life might be intelligent. Some of those intelligences might have developed technology. Some of those technologies might include space travel. The odds sound good until you do the math. Even if intelligent civilizations are common, the distances between stars are so vast that the odds of one of those civilizations randomly encountering Voyager 2 are effectively zero. Voyager 2 is not aimed at any particular star. It is flying through interstellar space on a trajectory that will not bring it close to another solar system for tens of thousands of years, and when it does pass near another star, it will be moving too fast to be captured by that star's gravity. It will just fly past, a tiny metal object drifting through the dark, unnoticed and unremarked. For Voyager 2 to be found, someone would have to be looking. They would have to detect the spacecraft from a distance, realize it was artificial, intercept it, and bring it aboard for study. That chain of events is so unlikely that it borders on impossible, and yet we sent the record anyway. Sagan knew the odds. He talked about them openly. He described the golden record as a message cast into the cosmic ocean with no guarantee that anyone would ever find it. But he also argued that the act of sending the message was valuable in itself, that it forced humanity to think about what we wanted to say, to reflect on who we are, to imagine a future where we might not be alone. The record is not just a message to aliens, it is a mirror, a way of looking at ourselves from the outside and asking what we want to be remembered for. There is also a cultural dimension to the record that is easy to miss. The selection process was dominated by Western scientists and artists. The music includes a lot of classical European compositions. The images include a lot of technology and infrastructure that reflects industrialized societies. The record was curated by a specific group of people at a specific moment in time, with specific biases and blind spots. It is not a neutral representation of humanity. It is a representation of humanity as seen by Carl Sagan and his team in 1977. Other people at other times would have made different choices. The record is not universal, it is particular, and that particularity is part of what makes it interesting. Critics have pointed out that the record is overly optimistic, that it presents a sanitized version of humanity that ignores our capacity for violence, cruelty, and destruction, that it is a propaganda piece designed to make us look good to potential alien observers. There is some truth to that. The record does not include images of war, poverty, pollution, or any of the darker aspects of human civilization. It is aspirational. It shows what we hope we are, not what we actually are. Whether that is dishonest or simply strategic is a matter of perspective. Sagan would have argued that if you are introducing yourself to an unknown intelligence, you lead with your best foot forward. You do not open the conversation with an apology. The fact that the record exists is also a political statement. The decision to include it on Voyager was not automatic. NASA had to approve it. The US government had to approve it. There were debates about whether it was appropriate to use public funds to send a message to hypothetical aliens when there were pressing problems on Earth. But the project moved forward anyway, and the record was included. That decision reflects a belief, however tentative, that reaching out to the universe is worth doing, that the search for connection, for meaning, for context in the cosmos is a legitimate use of resources and attention. Not everyone agreed then, not everyone agrees now. But the record is there, bolted to the side of Voyager 2, flying through interstellar space, because someone decided it mattered. The legacy of the golden record extends beyond the physical artifact. It has become a cultural icon, a symbol of humanity's desire to reach beyond itself, to communicate, to connect, to be known. The record has been referenced in books, films, television shows, songs. It has inspired art projects, museum exhibits, educational programs. People who have never heard the actual contents of the record still know what it represents. a message in a bottle, a greeting to the stars, a reminder that we once looked up and wondered if anyone was looking back. And now Voyager 2 is 15 billion miles from Earth, flying deeper into interstellar space with every passing second. The spacecraft is dying. The power is fading. The instruments are being shut down one by one. Within the next decade, Voyager 2 will no longer be able to transmit. It will go silent, and when that happens, the only part of the mission that will still be functioning is the golden record. The disk will still be there. The images will still be encoded in the grooves. The music will still be playable, if anyone ever figures out how to play it. The record will outlive the spacecraft. It will outlive the mission. It will outlive everyone who worked on it. And it will keep flying, carrying humanity's message for millions of years, maybe longer, maybe forever. The golden record is not going to be found. The odds are too low. The distances are too vast. The galaxy is too big, and Voyager 2 is too small. But that does not make the record meaningless. It makes it something else, a testament, a gesture, a statement that even in the face of impossible odds, we reached out anyway, we tried to connect, we tried to say something that mattered, and whether or not anyone ever hears it, the fact that we sent it says everything about who we are, about our hope, our curiosity, our refusal to accept that we are alone, about the fact that we looked up at the stars and decided that even if no one is listening, we still have something to say. 300,000 years, that is how long it will take Voyager 2 to cross the Oort Cloud. Not 300 days, not 300 years, 300,000 years. Picture that timeline if you can. Anatomically modern humans have only existed for about 300,000 years. The earliest stone tools date back maybe 3 million years. 300,000 years ago, Homo sapiens was just beginning to spread out of Africa. There were no cities, no agriculture, no written language, no wheel, nothing remotely resembling modern civilization. And Voyager 2 will spend that entire span of time, the entire length of our species' existence on Earth, drifting through a single region of space we have never seen and will probably never visit. 300,000 years from now, if there are still humans around, they will not resemble us. The languages we speak will be dead. The nations we live in will be gone. The technologies we use will be incomprehensible relics. And somewhere out there in the dark, moving at 9.6 miles per second, Voyager 2 will still be flying. Silent, powerless, frozen solid. A tomb carrying a message from a species that may no longer exist. That is the future we are talking about when we talk about Voyager 2's journey through the Oort Cloud. Not a future anyone alive today will see. Not a future anyone's grandchildren or great-grandchildren or great-great-great-grandchildren multiplied 1,000 times over will see. A future so distant that it stops feeling like a future at all and starts feeling like geology, like the slow drift of continents, like the erosion of mountains, like the kind of time scale where species evolve and die and the planet itself changes shape. The Oort Cloud is not a cloud in any normal sense of the word. It is not a nebula. It is not a gas. It is not even particularly dense. It is a vast spherical shell of icy objects, mostly comets, that surrounds the entire solar system at a distance so extreme that calling it remote does not capture the scale. The Oort Cloud starts somewhere around 2,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. 2,000 astronomical units is 186 billion miles. Voyager 2 is currently about 12.5 billion miles from Earth, which sounds like a lot until you realize It has only covered about 7% of the distance to the inner edge of the Oort Cloud. It has been flying for nearly 50 years and it is still in the neighborhood. It has not even left the driveway yet. The outer edge of the Oort Cloud is even more absurd. Most estimates place it somewhere between 100,000 and 200,000 astronomical units from the Sun. That is roughly 1 to 2 light-years, half the distance to the nearest star. The Oort Cloud is so large that it takes up a significant fraction of the space between our Sun and the next solar system over. It is not part of the solar system in the way we normally think about it. It is not a set of planets orbiting in neat circles. It is a halo, a shell of debris left over from the formation of the solar system 4.5 billion years ago, pushed out to the edge of the Sun's gravitational influence and frozen in place. And Voyager 2 is going to spend 300,000 years crossing it. At 9.6 miles per second, that is 34,560 miles per hour. Fast by any human standard. Fast enough to cross the continental United States in less than 5 minutes. And at that speed, crossing the Oort Cloud will take longer than recorded human history has existed, longer than the pyramids have stood, longer than the last ice age, longer than the time since Neanderthals went extinct. The objects in the Oort Cloud are mostly small. Comets, really, chunks of ice and rock ranging from a few hundred meters across to maybe a few tens of kilometers. They are spread out over such a vast volume of space that the average distance between them is measured in tens of millions of miles. The Oort Cloud is not crowded. It is not dense. It is not a hazard to navigation in the way an asteroid belt might be. If you were somehow sitting on Voyager 2 as it drifted through the Oort Cloud, you would see nothing, no nearby objects, no comets streaking past, just the same black void you see everywhere else in interstellar space. The nearest comet might be 10 million miles away. You would never know it was there. And that is the strange thing about the Oort Cloud. It is enormous, but it is also mostly empty. It contains billions, maybe trillions of objects, but they are so spread out that the total mass of the entire cloud is probably only a few times the mass of Earth. All that volume, all that space, and there is barely anything in it. The Oort Cloud is a graveyard, a fossil, a relic of the solar system's formation that has been sitting out there untouched for billions of years, and Voyager 2 is going to pass through it without ever seeing a single object up close. The reason the Oort Cloud exists at all is because of Jupiter and Saturn. When the solar system was forming, the giant planets were still migrating. Their gravity was pulling in material from the surrounding disk of gas and dust, and anything that got too close but did not quite fall into the planets got flung outward. Comets, ice chunks, rocky debris, all of it got kicked to the edge of the solar system by gravitational interactions with the gas giants, and that material settled into a roughly spherical shell at the outer limits of the Sun's gravitational reach. Over time, the orbits stabilized, the objects stopped moving inward, and the Oort Cloud became what it is today, a frozen reservoir of primordial material sitting at the edge of the Sun's influence, waiting for the occasional gravitational nudge from a passing star to send one of its members careening back toward the inner solar system as a new comet. That is where long-period comets come from, by the way. The ones with orbital periods measured in thousands or millions of years. They start in the Oort Cloud. Something perturbs their orbit, maybe a passing star, maybe a density wave in the galaxy, and they fall inward toward the Sun. They heat up, the ice sublimates, they grow a tail, they become visible from Earth. We see them streak across the sky, and then they swing back around the Sun and head back out to the Oort Cloud, where they will stay for another 10,000 years until the next nudge sends them inward again. Voyager 2 will never see any of that. By the time it reaches the Oort Cloud, it will have been dead for tens of thousands of years. The spacecraft will have no power, no instruments, no transmitter, no way to record what it is seeing. It will be a hunk of metal and plastic and gold plating, drifting through the dark, obeying the laws of motion, seeing nothing, recording nothing, saying nothing. A tomb, a monument, a message in a bottle that will never be opened. NASA knows this. They have run the projections. By the early 2030s, Voyager 2 will not have enough power to run a single science instrument. By 2036, the signal will be too weak for the Deep Space Network to detect. After that, silence. The spacecraft will keep flying, but Earth will no longer be able to hear it, and Voyager 2 will no longer be able to hear Earth. The connection will be severed permanently, and the spacecraft will drift into the Oort Cloud alone, unobserved, unreachable, carrying the memory of a planet it will never see again. The timeline is staggering. Voyager 2 crossed into interstellar space in 2018. It is currently about 12.5 billion miles from Earth. The inner edge of the Oort Cloud is roughly 2,000 astronomical units away, which translates to about 186 billion miles. At 9.6 miles per second, Voyager 2 will reach the inner edge of the Oort Cloud in about 300 years. Not 300,000. 300. That is the 24th century. The year 2300, give or take a few decades depending on where you draw the boundary. By then, everyone alive today will be long dead. The political systems we live under will have changed. The technologies we use will be obsolete. But 300 years is still within the realm of human history. We can imagine it. We can picture it. We have records going back further than that. The outer edge of the Oort Cloud, though, that is where the timeline stops making sense. If the outer edge is at 100,000 astronomical units, which is a conservative estimate, Voyager 2 will not reach it for another 300,000 years, 300 millennia, and the whole time it is crossing that region, the spacecraft will be dead. It will have been dead for 299,700 years by the time it exits the other side. NASA will not be there to track it. Earth will not be listening. There will be no one watching, no one recording, no one celebrating the moment it finally clears the Oort Cloud and enters true interstellar space, the empty void between stars where even the faint gravitational tug of the sun no longer matters. That is the concept of never completing alive. Voyager 2 will pass through the Oort Cloud as a corpse. It will enter the cloud under its own power, coasting on the momentum it built up during the planetary flybys in the 1980s, and it will exit the cloud 300,000 years later, still coasting, still moving, still obeying Newton's laws, but with no power, no instruments, no ability to tell anyone what it saw. The mission will be over. The spacecraft will have become an artifact, a relic, a piece of 21st century technology drifting through a region of space that will not look any different 300,000 years from now than it does today. And here is the thing that makes it even stranger. The Oort Cloud is not a destination. It is not a place you go to. It is a region you pass through. And passing through it takes so long that by the time Voyager 2 exits the other side, the stars themselves will have moved. The constellations we see in the night sky will be different. The sun will have drifted to a different position in the galaxy. The local interstellar cloud, the region of space our solar system is currently passing through, will be long gone. The sun will have entered a different cloud with different density, different temperature, different conditions, and Voyager 2 will still be flying, carrying a golden record with music and images and greetings from a planet that may no longer exist. The scale is almost impossible to grasp. Voyager 2 is 12.5 billion miles from Earth right now. That is far. That is unimaginably far. But it is also nothing compared to the distance it will eventually cover. By the time it exits the Oort Cloud, it will be 2 light-years from the Sun. 2 light-years. Light itself takes 2 years to cover that distance. Voyager 2, traveling at 9.6 miles per second, will take 300,000 years, and even then, it will still be in the Sun's neighborhood. It will still be orbiting the Milky Way along with the Sun and every other star in the local stellar group. It will not have escaped. It will not have reached another star. It will just be further away than any human-made object has ever been, or ever will be, until we build something faster. The trajectory beyond the Oort Cloud is equally strange. Voyager 2 is not aimed at any particular star. It is not heading toward Alpha Centauri, the nearest star system, which is 4.3 light-years away. It is not heading toward any known exoplanet. It is just flying in a direction. That direction happens to be toward the constellation Telescopium, a faint group of stars in the southern sky that no one outside of astronomy has ever heard of. And it will keep flying in that direction for millions of years, drifting through the empty space between stars, covering distance that sounds impressive by human standards but is a rounding error on the scale of the galaxy. The Milky Way is about 100,000 light-years across. Voyager 2 is currently about 12.5 billion miles from Earth, which is roughly 0.002 light-years. It would take Voyager 2 about 20,000 years to travel 1 light-year at its current speed. To cross the entire galaxy from one edge to the other would take 2 billion years. 2 billion, that is half the age of the Earth. That is longer than multicellular life has existed on this planet. And Voyager 2 is not even trying to cross the galaxy, it is just drifting, following its trajectory, obeying gravity, moving at 9.6 miles per second through a galaxy that does not care and will never notice. And the galaxy itself is moving. The Milky Way is part of the local group, a collection of galaxies that includes Andromeda, Triangulum, and a few dozen smaller galaxies. The local group is drifting through space as part of the Virgo supercluster, which is itself part of the larger cosmic web. Everything is moving. Everything is drifting, and Voyager 2 is drifting with it, a tiny speck of metal and plastic and human ambition, following the currents of gravity through a universe that is larger than any human brain can fully comprehend. NASA has described Voyager 1 and Voyager 2 as destined, perhaps eternally, to wander the Milky Way. That phrase, perhaps eternally, is doing a lot of work, because the spacecraft are not eternal. They are already dying. The power is fading. The instruments are shutting down. The transmitters will go silent within the next decade, and after that, the spacecraft will be inert. They will still be flying, yes, but they will not be doing anything. They will just be objects, passive, silent, drifting, and they will keep drifting for as long as the laws of physics allow, which is effectively forever. The spacecraft could last for billions of years. The structure is solid. The materials are durable. The golden record is protected by an aluminium case that should survive radiation, temperature extremes, and micrometeorite impacts for 1 billion years or more. But eventually, something will hit Voyager 2 hard enough to damage it, or the radiation will degrade the electronics beyond recognition, or the spacecraft will drift too close to a star and get vaporized, or it will be captured by a black hole and torn apart by tidal forces, or, most likely, it will just keep flying forever, slowly accumulating damage, slowly breaking down, until it is no longer recognizable as a spacecraft. Just a cloud of metal and plastic and gold dust, spread out over millions of miles, drifting through the galaxy, carrying no message, no memory, no trace of the civilization that built it. That is the eventual fate of Voyager 2. Not a glorious end, not a dramatic collision, not a discovery by an alien civilization that decodes the golden record and marvels at the ingenuity of humanity. Just a slow, quiet disintegration over timescales so long that the word slow stops having meaning. The spacecraft will drift through the Oort Cloud for 300,000 years. It will drift through the empty space beyond the Oort Cloud for millions of years. And it will keep drifting, following its orbit around the galactic center for billions of years, until eventually the Milky Way itself collides with Andromeda and the entire structure of the galaxy changes. And even that is not the end, because after the Milky Way and Andromeda merge, the resulting galaxy will keep existing. And Voyager 2, if it somehow survives the collision, will keep drifting through the new galaxy, through the spaces between galaxies, through whatever comes next, until the universe itself reaches heat death, and there is nothing left but cold, empty space and the faint remnants of particles that have long since stopped interacting with anything. And even then, Voyager 2 might still be there, a frozen relic, a monument to a species that once looked up at the stars and decided to reach for them. The cosmic scale of this journey is almost offensive. Voyager 2 is the most distant human-made object still in contact with Earth. It has traveled further than anything we have ever built. It has visited more planets than any other spacecraft. It has sent back more data, covered more distance, survived longer than anyone expected. And by every human measure, it is a triumph, a success, a machine that has outlived its design life by a factor of 10 and is still going. But on the scale of the galaxy, Voyager 2 is nothing. It is invisible. It is a speck, a grain of sand on a beach that stretches for thousands of miles, a single atom in a raindrop in an ocean the size of a planet. The spacecraft has been flying for nearly 50 years, and it has barely left the solar system. It is 12.5 billion miles from Earth, which sounds enormous until you realize that is only 0.002 light-years. The nearest star is 4.3 light-years away. Voyager 2 would take 80,000 years to get there at its current speed, and it is not even headed in that direction. It is flying sideways through the galaxy, away from the nearest stars, toward a patch of empty space that will remain empty for longer than our species will probably exist. And that is the paradox. Voyager 2 is humanity's greatest ambassador to the cosmos. It is the furthest we have ever reached, the longest we have ever maintained contact with a machine, the most data we have ever collected from beyond the edge of the solar system. And it is also utterly insignificant, a tiny, fragile, temporary artifact, drifting through a universe so large that the entire history of human civilization, from the first stone tools to the present day, is a blink, a flicker, a moment so brief that it barely registers. Voyager 2 will spend 300,000 years crossing the Oort Cloud, and during that entire span, nothing will change. The objects in the Oort Cloud will keep drifting in their orbits, just as they have for billions of years. The sun will keep burning, just as it has for billions of years. The galaxy will keep rotating, just as it has for billions of years. And Voyager 2 will keep flying, silent and powerless, a relic of a species that once built machines and sent them into the dark with the hope that someone, somewhere, might find them and understand. But no one will find Voyager 2 in the Oort Cloud. No one will be watching. No one will be listening. The spacecraft will pass through that region alone, unseen, unrecorded, carrying a message that will never be delivered. And when it finally exits the Oort Cloud 300,000 years from now, it will enter the true void, the empty space between stars, the the darkness that fills 99.999% of the universe, and it will keep flying, not because it has a destination, not because it has a purpose, but because the laws of physics say that an object in motion stays in motion and there is nothing in interstellar space to stop it. That is the future of Voyager 2, not a future anyone alive today will see, not a future anyone's descendants will see for thousands of generations, but a future that is already written, already inevitable. The spacecraft is on its trajectory, the power is fading, the instruments are shutting down, and within a few years the connection with Earth will be severed forever. Voyager 2 will become a ghost, a silent traveler, a monument to a moment in human history when we looked up at the stars and decided that distance did not matter, that time did not matter, that the impossible odds of ever making contact with another intelligence did not matter. We sent a message anyway. We built a machine and filled it with music and images and greetings and launched it into the void. And now that machine is 15 billion miles away, still flying, still carrying our message, and still heading toward a future so distant that it stops feeling real. The Oort Cloud is not the end of Voyager 2's journey. It is just the beginning of the longest, loneliest stretch. A 300,000-year crossing through a region of space we have never seen and will probably never visit. And after that, millions more years drifting through the void, following the currents of gravity, moving at 9.6 miles per second through a galaxy that we'll never notice and a universe that we'll never care. That is the legacy we are building, not a grand discovery, not a triumphant return. Just a quiet, slow, eternal drift through the dark. A machine that once talked to Earth, carrying the memory of a planet it will never see again, flying deeper and deeper into the infinite until time itself loses meaning and the only thing left is motion. Endless, purposeless, unstoppable motion through a cosmos that will outlast everything we have ever built and everything we will ever build forever. 300,000 years. That is how long Voyager 2 will spend crossing the Oort Cloud, and during that entire span, longer than our species has existed in its current form, the spacecraft will be dead, not broken, not destroyed, just silent. A hunk of metal and plastic and gold plating drifting through the dark at 9.6 miles per second, carrying a message no one will ever read, following a trajectory no one will ever track, moving deeper into a void so vast that distance stops having meaning and time becomes a measurement of nothing. That is the future we have been building toward. Not a dramatic finale, not a blaze of glory, just a slow, quiet fade into a darkness that will outlast everything we have ever built and everything we will ever build. Voyager 2 will keep flying long after the last person who remembers its launch has died, long after the nations that funded it have collapsed or transformed into something unrecognizable, long after the languages spoken by the voices on the golden record have gone extinct. And it will keep flying not because it has a purpose, but because an object in motion stays in motion and there is nothing in interstellar space to stop it. This is the legacy we are leaving, not a grand discovery, not a triumphant return. Just a machine that once talked to Earth, now silent, now alone, now unreachable, drifting through the cosmos on a journey that will never end because the universe does not offer endings, only distance, only time. Only the cold, patient mathematics of gravity and momentum playing out across scales so large that human minds cannot hold them. And yet, for all the loneliness, for all the silence, for all the staggering indifference of the cosmos, Voyager 2 matters, not because it will be found, not because the golden record will ever be played, Not because some alien intelligence will intercept the spacecraft and decode our message and marvel at our ingenuity. It matters because we built it, we sent it. We reached across 15 billion miles of empty space and touched something we could never see with our own eyes. We built a machine that outlived its design life by a factor of 10 and is still going. We made something that will last longer than our civilization. And that act, that gesture, that refusal to accept the limits of what is possible says more about who we are than any message etched into gold ever could. Start with the numbers, because the numbers are the easiest part to grasp, even if they are almost impossible to believe. Voyager 2 launched on August 20, 1977. It has been flying for nearly 50 years. In that time, it has traveled more than 12.5 billion miles. It has visited Jupiter, Saturn, Uranus, and Neptune, 4 planets, each one a world in its own right. Each one with moons, rings, atmospheres, magnetic fields, weather patterns more extreme than anything on Earth. Voyager 2 mapped them, photographed them, measured their temperatures, their radiation levels, their gravitational fields. It sent back thousands of images, tens of thousands of data points, information that changed how we understand the outer solar system. Information that revealed volcanoes on Io spewing sulfur into space, geysers on Enceladus, the hexagonal storm at Saturn's North Pole, the tilted magnetic field of Uranus, the supersonic winds of Neptune. Every single one of those discoveries was made by a machine the size of a small car, powered by plutonium, built with 1970s technology, operating on a power budget smaller than a refrigerator light bulb. A machine that was designed to last 5 years and has now been running for nearly 50. That alone is a triumph. That alone is worth celebrating. And everything that came after, the crossing of the heliopause, the entry into interstellar space, the measurements of the interstellar plasma, the detection of galactic cosmic rays, all of that is bonus. Science we were never supposed to get, data that was never part of the original mission, a gift from a machine that refused to die when it was supposed to. But the numbers are not the whole story, because the real legacy of Voyager 2 is not just what it discovered, it is what it represents. Voyager 2 is a statement, a declaration, a refusal to accept that the universe is too large, too cold, too indifferent for humanity to make a mark. We looked up at the stars and we decided that distance did not matter, that time did not matter, that the impossible odds of success did not matter. We built a machine and we launched it into the void with the full knowledge that it would eventually stop talking to us, stop sending data, stop being anything other than a silent artifact drifting through the dark. And we did it anyway, because the act of trying matters, because reaching matters, because the gesture of sending a message, even if no one ever hears it, is worth doing. That is what Voyager 2 is, not just a spacecraft, not just a scientific instrument, a symbol, a monument, a reminder that we are a species that builds things that last longer than we do, that we send pieces of ourselves into the cosmos even when we know we will never see them again, that we reach for the stars not because it is practical, not because it is profitable, but because we are curious, because we want to know, because we refuse to accept that we are alone in the universe, and even if we are, we want to leave a trace, a mark, a sign that we were here, that we made something, that we tried. The emotional weight of that is hard to describe, because Voyager 2 is not alive, it is a machine. It does not feel, it does not think, it does not care whether we remember it or forget it. And yet when we talk about Voyager 2, when we describe its journey, when we watch the power fade and the instruments shut down one by one, it feels like grief, real grief. The kind you feel when someone you love is dying and there is nothing you can do to stop it. We are mourning a machine. We are watching it die in slow motion. And we are powerless to change the outcome, because the power budget is fixed, the plutonium decay rate is fixed, the laws of physics are fixed, and all we can do is make the best decisions we can with the time we have left, knowing that no matter what we do, the end is coming. That grief is not irrational, it is not sentimental, it is a recognition of what Voyager 2 actually is, a vessel, a carrier, a piece of us. The spacecraft is not just metal and electronics, it is the work of thousands of people over decades. Engineers, scientists, technicians, programmers, administrators, people who spent their entire careers keeping this machine alive, people who have poured their lives into a project that will outlast them. People who will die knowing that Voyager 2 is still out there, still flying, still carrying their work into the galaxy long after they are gone. That is what we are mourning when we mourn Voyager 2. Not the machine, the people, the effort, the dream, the audacity of believing that we could send something beyond the solar system and that it would matter. And it does matter. It mattered to the engineers at the Jet Propulsion Laboratory who scrambled in August 2023 when Voyager 2 went silent after a 2-degree antenna pointing error. For 2 weeks they did not know if the spacecraft was dead. They did not know if the mission was over. They searched for a signal. They adjusted the deep space network antennas. They recalculated trajectories. They waited. And when they finally detected a faint carrier signal on August 1, the relief was real. The spacecraft was still alive, still transmitting, just pointing the wrong way. And they had one shot to fix it, one command, 37 hours round trip. If it worked, contact would be restored. If it did not, the mission would end, not because the spacecraft failed, because humanity lost the ability to hear it. They sent the command. It worked. Full contact restored. And for a brief moment, the people who had spent their careers nursing this machine through 50 years of spaceflight allowed themselves to feel something that does not get talked about much in engineering circles. Joy, relief, pride. The knowledge that they had just saved a mission that should have ended decades ago. That they had kept a connection alive across 12.5 billion miles of empty space, that they had refused to let go. That is what makes Voyager 2 human, not the spacecraft itself, the people behind it, the people who built it, the people who operate it, the people who stay up late tracking it, debugging it, making decisions about which instruments to turn off and which ones to keep running a little longer. The people who know that within the next few years the power will drop below the threshold where contact is possible and the spacecraft will go silent forever, and they are doing everything they can to delay that moment, to stretch the mission as far as it will go, to make sure that when Voyager 2 finally stops talking, it does so having given humanity every bit of data it was capable of collecting. But the silence is coming. And when it arrives, it will be permanent. There will be no dramatic final transmission, no countdown, no last words. One day, the Deep Space Network will point its massive antennas at the coordinates where Voyager 2 is supposed to be, and they will hear nothing. Static, the background hiss of the galaxy. And somewhere out there, 15 billion miles away, and getting further with every passing second, the spacecraft will still be flying, still intact, still obeying the laws of motion, but no longer able to tell anyone it exists. That silence will not be an ending, it will be a transformation. Voyager 2 will stop being an active mission and become something else, an artifact, a time capsule, a monument, a message. The golden record will still be there, bolted to the side of the spacecraft, protected by an aluminium case, carrying sounds and images and greetings from a planet the spacecraft will never see again. The music will still be etched into the grooves. The diagrams will still be accurate. The pulsar map will still point back to Earth, assuming whoever finds it understands pulsars and cares enough to trace the origin. The record will outlast the mission. It will outlast the spacecraft's ability to transmit. It will outlast everyone who worked on it, and it will keep flying, carrying humanity's message for millions of years, maybe longer, maybe forever. And that is the legacy. Not the science, though the science is extraordinary. Not the images, though the images are beautiful. Not the data, though the data has rewritten textbooks. The legacy is the record, the statement, the gesture, the fact that we looked up at the cosmos, saw the vast indifferent darkness, and decided to send a greeting anyway. We knew no one would probably hear it. We knew the odds of the spacecraft ever being found were functionally zero. We knew that even if someone did find it, they might not be able to decode it. And we sent it anyway. Because the act of reaching out, the act of trying to connect, the act of saying we are here and we made this and we hope you find it, is worth doing even when the outcome is uncertain, especially when the outcome is uncertain. That is what it means to be human. To build things that last longer than we do, to send messages we will never hear answered, to reach for the stars knowing we will never touch them, to explore not because it is easy, not because it is profitable, but because we are curious, because we want to know what is out there, because we refuse to accept that the universe is too large for us to make a mark. Voyager 2 is that mark. A tiny, fragile, temporary mark on a cosmos that will outlast everything, but a mark nonetheless, proof that we were here, that we looked up, that we tried. The spacecraft is now more than 12.5 billion miles from Earth. It is moving at 9.6 miles per second relative to the Sun. At that speed, it would take about 19,400 years to travel 1 light year. The nearest star is 4.3 light-years away. Voyager 2 would take more than 80,000 years to reach it, and it is not even headed in that direction. It is flying toward the constellation Telescopium, a faint group of stars in the southern sky that most people have never heard of. And it will keep flying in that direction for millions of years, drifting through the empty space between stars, covering distance that sounds impressive by human standards, but is barely noticeable on the scale of the galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. Voyager 2 will drift past a tiny fraction of them. It will not visit another solar system. It will not land on another planet. It will not be captured by the gravity of another star. It will just keep flying, following its orbit around the galactic center, moving at 9.6 miles per second through a galaxy that is rotating at 500,000 miles per hour. The spacecraft is a passenger, a piece of cosmic debris, a speck of dust on a current so large that even the word current feels inadequate. Voyager 2 is drifting through the Milky Way the way a leaf drifts down a river. Except the river is 100,000 light-years wide, and the leaf will keep drifting for billions of years. And during that entire journey, the spacecraft will be alone. It will not see another human-made object. It will not receive another command from Earth. It will not transmit another signal. It will be silent, powerless, frozen solid. A tomb carrying a message from a species that may no longer exist by the time anyone ever reads it. That is the future we have built. That is the legacy we are leaving. A machine that once talked to Earth, now silent, now drifting, now carrying the memory of a planet it will never see again. But silence is not the same as meaninglessness. Voyager 2 will still matter even after the transmitter goes dark. It will matter because it is still there, still flying, still carrying the golden record, still obeying the laws of physics, still proving that we built something that could survive the journey from Earth to interstellar space and keep going. The spacecraft is a testament to human ingenuity, to human perseverance, to the refusal to accept limits, to the belief that we can build things that outlast us, that we can send pieces of ourselves into the cosmos and that those pieces will endure long after we are gone. That is not nothing. That is not insignificant. That is everything. Because in a universe as vast and as indifferent as ours, the only meaning that exists is the meaning we create. And Voyager 2 is meaning. It is a statement, a declaration, a refusal to accept that we are small, that we are temporary, that we do not matter. We built a machine and we sent it into the void. We filled it with music and images and greetings and launched it toward the stars with the full knowledge that it would probably never be found. And we did it because we wanted to, because we could. Because the act of reaching out, the act of saying we are here, the act of sending a message into the darkness with the hope that someone might hear it, is worth doing. That is the legacy of Voyager 2, not the science, not the data, not the images, the fact that we tried, the fact that we reached, the fact that we refused to accept that the universe is too large for us to make a mark. And we did make a mark. Voyager 2 is that mark, a tiny, fragile, temporary mark on a cosmos that will outlast everything we have ever built and everything we will ever build. But a mark nonetheless, proof that we were here, that we looked up, that we wondered what was out there, that we built machines and sent them into the dark to find out, that we cared enough to try, that we believed, however tentatively, that we might not be alone. That somewhere out there in the vast dark there might be someone else looking up at their sky and wondering the same thing. And even if there is not, even if we are alone, the fact that we asked the question matters, the fact that we sent a greeting matters, the fact that we reached out into the void and said hello matters. That is what Voyager 2 is, a greeting, a message, a hope, a dream. A machine built by people who believed that distance did not matter, that time did not matter, that the impossible odds of success did not matter. We built it, we launched it, we watched it fly past Jupiter, Saturn, Uranus, Neptune. We watched it cross the heliopause and enter interstellar space. We watched it send back data from a region of the cosmos no human-made object had ever reached. And now we are watching it die. Slowly, quietly, one instrument at a time, and we are mourning it, not because it failed, because it succeeded so completely that it flew beyond the point where we could follow. And when the last signal fades, when the deep space network hears nothing but static, when the connection is finally severed and Voyager 2 becomes unreachable, that will not be the end. It will be a transformation. The spacecraft will stop being an active mission and become something else, a monument, a time capsule, a message in a bottle, drifting through the cosmic ocean, waiting for someone to find it. And even if no one ever does, even if the golden record is never played, even if the spacecraft drifts through the galaxy for billions of years and is never seen by another intelligence, it will still matter. Because we sent it, because we tried, because we refused to accept that the universe is too large for us to make a mark. Voyager 2 is that mark, and it will endure, silent, alone, unreachable, but enduring nonetheless. A testament to human curiosity, human ingenuity, human perseverance, a reminder that we once looked up at the stars and decided to reach for them, that we built a machine and filled it with music and images and greetings and launched it into the void, that we cared enough to try, that we believed, however tentatively, that we might not be alone, that we wanted to be known, that we wanted to be remembered, that we wanted to leave something behind that would outlast us. And we did. Voyager 2 is that something, a machine that once talked to Earth, now silent, now drifting, now carrying the memory of a planet it will never see again. A machine that will keep flying for millions of years, long after the last person who remembers its launch has died, long after the nations that funded it have collapsed, long after the civilizations that built it have changed beyond recognition. A machine that will drift through the Oort Cloud for 300,000 years, through the empty space beyond for millions more, following its orbit around the galactic center for billions of years, until eventually the Milky Way itself collides with Andromeda and the entire structure of the galaxy changes. And even then, Voyager 2 might still be there, a frozen relic. A monument to a species that once looked up at the stars and decided to reach for them. That is the legacy. Not a discovery, not a triumph, not a dramatic finale, just a quiet, slow, eternal drift through the dark. A machine that once talked to Earth, now silent, now alone, now unreachable, carrying a message no one will probably ever read, following a trajectory no one will ever track, moving deeper and deeper into a void so vast that distance stops having meaning and time becomes a measurement of nothing. And it will keep flying, not because it has a purpose, not because it has a destination, but because an object in motion stays in motion, and there is nothing in interstellar space to stop it. Voyager 2 will drift through the cosmos for as long as the laws of physics allow, which is effectively forever. And when the last star burns out, and the universe reaches heat death, and there is nothing left but cold, empty space, and the faint remnants of particles that have long since stopped interacting with anything, Voyager 2 might still be there, a frozen monument, a silent traveler, a message from a species that once looked up at the stars and decided that even if no one was listening, we still had something to say. And we did say it. We said it with music, we said it with images, we said it with greetings in 55 languages, we said it by building a machine that could survive the journey from Earth to interstellar space and keep going. We said it by refusing to accept that the universe is too large for us to make a mark. We said it by reaching out into the void and saying, "We are here, we made this, we hope you find it. We hope you understand. And even if you do not, even if you never find it, the fact that we sent it matters, because the act of reaching out, the act of trying to connect, the act of sending a message into the darkness with the hope that someone might hear it, is worth doing. That is the legacy of Voyager 2. Not the science, not the data, not the images, the fact that we tried, the fact that we reached, the fact that we refused to accept that we are small, that we are temporary, that we do not matter. We built something that will outlast us. We sent a piece of ourselves into the cosmos. And it will keep flying, carrying our message for as long as the universe allows. Silent, alone, unreachable, but enduring nonetheless. A testament to human curiosity, human ingenuity, human perseverance. A reminder that we once looked up at the stars and decided to reach for them, that we built a machine and filled it with hope and launched it into the void, that we cared enough to try, that we believed, however tentatively, that we might not be alone, that we wanted to be known, that we wanted to be remembered, that we wanted to leave something behind, and we did. Voyager 2 is that something, a machine that once talked to Earth, a machine that will drift through the galaxy for billions of years, a machine that will carry the memory of a planet it will never see again, a machine that will keep flying, silent and powerless, through a cosmos that will outlast everything, a machine that will endure forever. Somewhere out there, 15 billion miles from the chair you are sitting in, a machine the size of a small car is drifting through the dark at 35,000 miles per hour. It has been flying for nearly 50 years. It will keep flying for millions more. And sometime in the next decade, possibly the next few years, it will stop talking. Not because it crashed, not because something broke, but because the plutonium heart that has kept it alive since 1977 will have decayed too far to power a transmitter. The signal will fade, the deep space network will hear nothing but static, and Voyager 2 will become unreachable, still there, still flying, still carrying the golden record, but silent, alone, beyond the point where we could ever follow. That is not a failure. That is the mission. We built a machine knowing it would eventually stop talking to us. We filled it with music and images and greetings and launched it into the void with the full knowledge that the odds of anyone ever finding it were functionally zero. And we did it anyway, because the act of reaching matters. Because the gesture of sending a message, even if no one ever hears it, is worth doing. Because we are a species that builds things that outlast us and refuses to accept that the universe is too large for us to make a mark. Voyager 2 is that mark, a tiny, fragile, temporary mark on a cosmos that will outlast everything. But a mark nonetheless, proof that we were here, that we looked up, that we wondered what was out there, that we cared enough to try. And when the last signal fades and the spacecraft drifts into silence, it will not be an ending, it will be a